This meeting is being recorded.
Okay, now let's wait for Miguel to connect to audio. All right, cool. Well, welcome everyone. My name is Carter Frost. I am geek extraordinaire, senior student troublemaker at Cabrillo College. And so today I'll be talking to you about a wide variety of different topics. Electrical engineering, robotics, computer science, computer information studies, computer engineering, a little bit about Arduinos. And unfortunately, because we're meeting in this online fashion, we won't be able to do any kind of activities. But what I'll try to do is I'll try to talk about what activities we would be doing, and hopefully what you would have learned from them. Yeah, so I apologize for that. The current climate is a little interesting. So yeah, so I've been in Cabrillo for quite a while. I've worked in the IT world, in cybersecurity, in private key infrastructures. I worked in manufacturing, shipping, and quality assurance. I've worked for companies in 5 different countries, doing a variety of things, and it's been a lot of fun. Just here at Cabrillo, I am a supplemental instructor for computer programming Java, and the last 2 years I've been teaching C++, as well as being the former president of the Robotics Club, and I'll talk about that in the next 2 slides. And I also have been a tutor and a data center technician here at Cabrillo, as well as a senator and the vice president of the student senate here. So that's just a little bit about me. I've been around a little bit. So if you ever have any questions about Cabrillo, if you need help with anything, trying to figure out what classes to take, or if you have any issues that need to be resolved and you're not sure who to go to, or if you need any kind of help, support, whether it's food, finance, or just emotional counseling or whatever, feel free to reach out to me. My email is e5 at carterfrost.com. That will automatically tag that that you're from Engineering 5. Yeah, so if you need anything, let's mute Miguel. There we go. So if you need anything, just let me know. I'm happy to help. Right now is some trying times, and even when things aren't this crazy, people still need help. So I'm always available. Okay, so let's talk about the Robotics Club a little bit. So if you want to join the Robotics Club, you can blast an email to cabrillo@gmail.com. Also, we have a Facebook group or page that try to keep updated with whatever material the club is up to at the time. And so here in the, let's see whose microphone is on. There we go. Okay. So here in the bottom left, we have Hopper here, which I in fact actually have her with me right now. Let's see if I as you can see, I have Hopper the robot with me today. And so this is the robot that, or the type of robot called a Swarmy that the Cabrillo Robotics Club has worked with for the last 3 years or so. And so they were a part of a competition called the Swarmathon, which the idea being is that there were these, that there was a swarm or multiple of these robots that would all be working collaboratively together to go out and collect resources and then to deliver them home. or to a nest, to a common location, and that all these robots had to work together with some very inferior sensors, and so there's a lot of struggle in overcoming that constraint of having bad sensors. And so my team last year was Darren Churchill here and Mike Butera. We had the previous year, we had a much bigger team. We had about 50 people, but we sort of, the last year, we boiled down to having 2 active members in the Swarmathon, with having a lot of other people in the club who are helping in support roles. But the code monkeys were primarily me. Mike Matera is an instructor at Cabrillo, and then Darren Churchill, who's a student at Cabrillo. And this is both of them at Kennedy Space Center. I actually was doing a camp with Roxanne, an engineering camp with Roxanne, while they were at Kennedy Space Center in Florida, picking up the award. And then up here we have Kiri. You may have seen Kiri in the STEM Center. If we ever get to reopen the STEM Center, you can go visit Kiri. She's this cute little robot that has a little laser in her chest that allows her to be able to see around where furniture is. And we'll talk a little bit more about sensors later. But she's just a little cute household robot. And so that's Kiri. And then this is sort of the kind of thing that the kind of reports, technical documents that we generated as a result of last year's competition for the Robotics Club. There's a lot going on. Up here we have the foraging strategy. This is essentially how the robot would wander around using a correlated random walk, which you can look that up on Wikipedia. Correlated random walk. It's essentially just pick a random direction, go a random distance, and then sort of keep going in that same direction-ish, as opposed to just randomly turning around and going backwards. Correlated just means that you tend to be going, traveling away from where you were. And so this is essentially our search pattern. Then we have our software features. This was essentially how we handled our behavior, which was unique from a lot of the other teams. And then one of the issues that we had, and that's this whole center of the document, was that one of the sensors that we were given had problems with it. And so one of the things that gave us the best advantage was that we were able to essentially in software figure out how to fix that hardware issue. And then we were able to automate testing and get an idea. So this was my role. All of this was my role of essentially figuring out whether or not we had a regression whenever we would make a change, that change would be a positive change. And I was able to run hundreds of simulations within 2 days, automated wise. So one of the developers would make a change and say, hey, Carter, could you test this out to make sure that it's good? And first I would look through the code, and then I would run my automated tests. I had a server stack at Cabrillo that's all they did for months. All that stack of servers did was run simulations and give me feedback on whether or not it was a good test, it was a good change or not. And sometimes there were instances where the code looked good, the physical behavior of the robot was really good, but maybe there was a side effect of being more careful when doing a particular action meant that we were going slower, and by going slower, we ended up scoring lower because we were moving too slow. And so there was a compromise. There's this fine compromise between we want to be able to collect as many cubes as possible, as carefully as possible, but that we want to minimize the risk, but we still want our score to be as high as possible. And so there were instances we would have meetings where all we were discussing was, yes, this code looks good, it's doing what it's supposed to do, but we see that our overall score ends up being hurt. It's lower because we are taking a more careful approach. And in the end, we actually ended up just in our driving around while we're in the forging, while we're searching around, we ended up going half the speed that all of the other teams were. And we were still able to just absolutely crush everyone. We got first place in the virtual rounds where the speed doesn't even matter in the virtual world. But we were still in the virtual competition. We were driving half the speed, and we collected twice. Our score was twice what the second place team was, and then we were like 10 times the third place team. So and then when it hit the physical competition, we did much better. Like we crushed. We absolutely crushed the other teams because we were so much more cautious. Because in the physical world, the sensors were a lot more flawed and a lot more likely to have noise. So yeah, so this was a kind of technical report that we would generate every year as part of the competition. This competition is over. Unfortunately, the money, the funding source that funded this competition was cut when Trump cut the Department of Education in NASA. But it was fun while it lasted. And actually, I am part of another NASA competition called the Space Robotics Challenge Phase 2. And I am working with the University of New Mexico. I'm actually on their team for the next two years or so. I'm on their team, and so we regularly telecommunicate. A lot of emails back and forth, and we share our code with GitHub and GitLab. So collaboration is really important. No matter what field that you're in, is being able to communicate to people over a great distance is an important skill to have. So all of you here are on Zoom, so you've taken the first steps to getting there. So that's good. Okay, so we're gonna do a few things. Let's start off with electrical engineering. And we'll build up to there. Any questions about me or about the Robotics Club so far? I have a totally separate slide on robotics in general. But if you have any questions about me or the Robotics Club, go for it.
If someone wants to join the Robotics Club,
yeah,
they need past experience doing that stuff, or do you learn while you're in it?
You can, yeah. So you can learn while you're in it. There's absolutely no experience required. I mean, we've had civil engineers in the club. We've even had people who just do construction. They're working on a construction degree, and that helps bring a different perspective to the club. So yeah, from any background is happily welcome. And I mean, just like right now, we're doing an AWS, so Amazon Deep Racer competition, which is driving around, essentially teaching a race car how to drive around a racetrack. That's what the club's doing right now. And the biggest problem to overcome has nothing to do with the code. The coding is actually very easy. There are plenty of people in the club that know how to code it. It's figuring out, drawing something on the whiteboard or physically, placing a car and saying, okay, the car sees this, what is the best action that it could take? And then figuring out how to sort of articulate that into words or draw a picture. That's the most difficult thing to actually to come up with, is like, how do we drive a car given this information? And that's a very human thing for somebody to be able to converse with. So a lot of the problems that we're facing in the club actually have nothing to do with coding. It's how do we go about with this kind of information? What do we do, or what is the best thing that the robot could do?
Thanks.
Yeah. Okay. Let's talk about electrical engineering. So, full disclaimer: I am not an electrical engineer. Electrical engineers are amazing people. They are incredibly brilliant. I just happen to do a lot of electrical stuff as a hobby, and for some reason, because I still have my eyebrows, people seem to trust me with electricity. Okay, so you might ask, well, what is electrical engineering? Anything that has to do with electricity is under the umbrella of electrical engineering. Seems silly, but that's just it. So any kind of electronics, Digital computers, power engineering, telecommunications, control systems, like the things that turn on and off water pipes, that's all under electrical engineering. Radio frequency engineering, signal processing, instrumentation, and microelectronics. If it uses electricity, it's electrical engineering. And so what we see a lot of the times is that people will have a background in electrical engineering, and you can pretty much work anywhere doing anything because pretty much everything uses electricity in some way. Whether you're an electrical engineer who's designing new farming implements, or if you're developing the next quantum computer, electrical engineering is going to be involved in some way. And I've worked on projects that they made the mistake of not bringing in an electrical engineer, and it caused a whole lot of problems because they were sort of just cobbling things together without an understanding of how components interacted with each other, and that caused all kinds of issues. Like one of the boards that I was working on looked something like this. Actually, it was this. This is the power distribution. Oh, let me turn on my pointer. This is a power distribution board for the Swarmy robot that I was just showing you. And the person who designed this board didn't really have any experience with electrical engineering. And they made one of these traces, one of these lines that you see, they made it thinner than the other one. And so what ended up happening was that when you applied the same voltage to both wheels, one wheel on the robot would spin faster than the other because the trace was thicker for one of the sides versus the other, and they didn't even catch that. It happened to be a student in Puerto Rico who I was talking with, that they were noticing that their robot was listing, and for us, our team, we just attributed that to our IMU not working properly. And so we were able to fix that with our IMU and also setting constant. We were measuring, we would tell the robot to drive a meter, and we would measure the distance that the robot would travel, and then also we would notice how much it listed, how much it turned to one side versus the other, and then we just put in a number constant to fix that. But one of the teams actually was able to look at these diagrams, who actually had a little bit of electrical engineering background, and was able to figure out that one of these traces was designed smaller than the other. So having an electrical engineer part of the process is really, really important. And so here's a robot that looks sort of like it's the same base that the Swarmy has. So yeah, as I said before, anything that uses electricity, computers, robots, cell phones, our credit cards, radars, navigation systems, any kind of wiring in buildings. And one of the nifty things about being an electrical engineer is you get all kinds of really nifty and very expensive toys to play with. We see a ton of very expensive Fluke digital voltmeter or multimeters. We see a very nice oscilloscope, some variable power supplies, another oscilloscope back there. You get lots and lots of equipment to test with. And so you can do a lot of different things, right? Anything that has to do with electricity, even things that you might not even associate with things that have to do with electricity, like software companies, right? eBay, we don't really consider eBay to be making physical things, but they have to have some knowledge of electrical engineering to perform their job. Maybe that they're selling things or that they're listing things in the store, and that they need an electrical engineer to go and actually make those breakdowns of those items. So pretty much any industry, if you are an electrical engineer, we've got work for you. So that's always a pretty safe bet. And I thought I had the slide somewhere here, but yeah, essentially, being an electrical engineer, not only do you only test things, but you are also, you could be in the designing process, and that could be literally just you throwing stuff on a whiteboard, and then having some intern then actually do the diagrams, do the thing that looks like this. That all you're doing is figuring out what components to buy and what are the tolerances of it. And so there's lots of different roles that you can be in as an electrical engineer. Okay. So, well, what exactly is electricity? So, it's essentially it is the force between charges. So what happens typically is that we have electrons, and the electrons really want to sort of balance themselves out. They want to spread out as much as possible. And so when we have two different forms of electricity. So yeah, I'll have examples for the different kinds, but that essentially the electrons want to balance themselves out. So just keep that in mind as we're going. So current electricity, we essentially in the battery, in the center core of the battery, or in the bottom specifically, there's a contact that has a ton of electrons, and then there's not really any on the positive side. And so what happens is that all the electrons want to get to the other side of the battery, but there's something in the battery that's shielding the electrons from just jumping through. And so if you connect a wire from one side of the battery to another side of the battery, then you have all the electrons that are flowing through the wire into the other side of the battery. And so if you just stick a wire there, then it's going to get really hot, and it's going to burn you, and it's going to be bad news bears. But what you can do is that you can stick things in between components, and that will allow you to do things with that electricity. So say for example, you stick a light bulb in between it, not like a household light bulb, but like an LED or something, some low voltage light bulb. It's going to light up as the electricity is passing through it. So yeah, so essentially imagine that this is the bottom of the battery and this is the top of the battery. The electrons really badly want to get from this side to this side. Yeah, so here's a diagram here. So essentially we have the cathode. This is essentially, hopefully there's not that many electrons here. And then we have the anode, which is essentially a ton of electrons. And then we have a separator that blocks them from just jumping directly into it. And so what happens is that if you connect a wire, then the electrons will happily go to this side. And essentially when your battery is dead, what that means is that the ratio or the balance of electrons is the same. That the anode and cathode, essentially their ratio or the balance of electrons is going to be the same. And so rechargeable batteries, you're essentially able to pump the electrons out and then put them back where they were. And anything that we stick between the wire, we could have something like a charger, which would act like a pump, where it would pump the electrons backwards. Or if we had a light, something that was consuming the power, it would allow the electrons to go this way. Cool. And so we have a few different kinds of power sources. Does anyone know what this first one is? What kind of power is that utilizing? Keep in mind you're all muted, so you have to unmute yourselves. Not quite. That's this one. What is this one? So what kind of energy? What is the energy in form of?
Or which one?
For the top left one.
It looks like a reservoir, almost like a potential energy, gravity.
The left one.
It looks like a pump, isn't it?
So where is it?
Looks like it's, maybe
on the bottom of the ocean floor.
It could be.
Or whatever.
Yeah. So yeah. Let's say that this pipe goes to the bottom of the ocean floor. And what kind of energy do we have in the ocean that's constant?
you have like currents.
Yeah, we have currents, and that would be down below the water. But what do you think that this giant floaty thing is using for energy? So if you're a surfer dude, these things are really important.
I think Mason said waves.
Yeah, giant waves, right? What happens is that as the waves go by, right, this yellow thing stays stationary, but this giant floaty thing rotates. It has a giant. It rotates right along here, and so as this goes up and down, you're generating energy. What about this guy? This middle top guy. We should all be very familiar with this guy because it's local.
That's Moss Landing, right?
Yeah, that's in Moss Landing. Do you know what they're doing in Moss Landing? How this is generating energy? So this is natural gas. They're burning natural gas, and that's generating electricity. So that's biomass, right? They're burning biomass, and all of this crazy plumbing is all to support that. And we're actually slowly converting some of the older turbines, because I think we only use like 2 of the 4 turbines. We're converting some of them to just be for power storage. So we're putting in essentially a giant Tesla Powerwall into the reactors that aren't being used. So just giant battery packs. Therefore, as we need power in emergencies, we have it stored in all of these batteries. And the reason why we don't see Moss Landing running all the time is that it's called a peaker plant. Only during peak times where there's a huge amount of usage do they power it up, and it's very, very expensive. So for example, if a ton of people are turning on their air conditioners all at 2 o'clock, it costs them $1 million just to spin this thing up for that 1 hour. So what ends up happening is that they would much more prefer to have rolling blackouts, right? They would, or that they send out messages telling everyone, hey, turn on your air conditioners during these times, try to conserve power, because they don't want to have to power up this giant power plant. So they would prefer to have rolling blackouts and whatnot. But if they see a sustained usage, like they see that maybe 4 or 5 hours over the day, that they need to be generating more power, then they'll power this thing up. And if they power it up, they'll tend to leave it running for at least a full day. Because if they just power up for an hour or 2, that doesn't really make sense. They just lost an incredible amount of money. And so if they power this up, then they're able to power down some of the other power plants to sort of balance out the load. And so yeah, so like this guy here, as David said, hydroelectric, right? We're using gravity. We're using all the water that's up here. It has a different potential energy than the water down here. And so what we're able to do is we're essentially able to drain the water down, and we have these giant turbines, essentially like giant fans that are spinning that generate electricity. And so what's great about this is that we're essentially using this water as a battery, that we're able to, when we have extra power, say that this peaker plant is running and generating more power than what's needed, we're able then to pump water up the hill with that extra water, and then when we need power, we're able to drain the water back down. And in some cases, I've been reading man, I totally brain farted. I was watching a documentary where they had enough rainwater that was coming up top, that essentially they never really needed to ever pump water back up. That the rainwater was pretty continuous, that they were running the turbines and draining the water as quickly as possible, and that was essentially sustaining power for a good portion of their country. And so this is considered very, very much renewable. Actually, all of these except for the biomass, because the water, right? When we use it, we can just pump it back up and use it again. I mean, of course, some of it's going to evaporate, but we're going to get more rain. And that's going to fill up this top reservoir. So what about these guys? We've probably seen these all over the place. The bottom left guys. What are these, and what do they get energy from?
Solar and wind.
Yeah, we got our solar panels here, and we've got our wind power and our wind turbine right here. And so, fortunately, in the last 10 years or so, we've actually broken even on solar panels. Originally, solar panels, if you made them, they would never generate as much energy as it took to manufacture them. But yeah, because well, the energy density in the sense of the materials and the manufacturing process. But now, not only are they much more efficient, the manufacturing process has become much more mainstream. Yeah, so now we've actually, huh?
Cheaper to make.
Yeah, it's cheaper to make. The material, we're able to use less materials, and the actual manufacturing process we've been able to simplify, so that's easier. The number of man hours, is reduced. Okay, cool. And then we've got our wind. That's really only practical for environments. Sorry about all the buzzing. Okay, there we go. This is only really practical in areas where we have high amounts of wind. And then what about this bottom center one?
It's like geothermal.
Yeah, it's geothermal. So it's essentially taking the difference in temperatures, and any difference in temperatures, and it's able to essentially create mechanical energy out of that, and then hook that up to a generator, and then dump that power on the power grid. And so in this case, it's taking the difference in temperature between a water source and some spot deep in the Earth's crust, but really you could take it from anywhere. So there's a few geothermal plants that they run off of the temperature of seawater, and then they run that seawater way inland where it's very, very hot, and just the difference in temperature where they are inland and the difference in temperature of the ocean where they're sucking it in is enough to be able to run the pump to suck in that water, run a full desalination plant, and then also provide any kind of mechanical energy that they need for some kind of manufacturing of food processing, making grain and whatnot. And there's a few instances of those in South America where they're not using them at all for electricity. They're just using them for mechanical energy to pump water in to essentially make it fresh water, and then also using it for other mechanical things. Like crushing things or whatnot. And then this bottom one here, these are batteries. And so a lot of batteries are literally just chemicals that happen to have that when they interact with each other, they give us power. And so a lot of the non-rechargeable batteries, when you manufacture them and you mix the chemicals the way that we do, whatever type they are, then they're going to inherently have those electrons in one spot and not in another spot. And when you connect them, it works. The electrons want to go get to the other side. And there are some of them actually, like hearing aid batteries. They may look like button batteries that are like in a watch, but they're actually different. They run solely on. They actually are chemicals that are activated by oxygen. So yeah, different kinds of power sources. So that was current electricity. So then we have static electricity. And And I'm sure that we've all played around with static electricity. You know, you rub your feet on the carpet and, you know, shock your friend on the nose or on the ear. And essentially it's that, you know, there's tons of electrons for whatever we consider our ground source. And what happens is that when you rub your feet on the carpet or whatnot, that you're essentially collecting all of those electrons. But then when you go to touch something like another person or some metal, that it doesn't have the same ratio of electrons. Right? The balance is different. Then what happens is that it wants to the electrons want to balance themselves out. Always remember that whether they're at a battery or if they're, you know, in a body of, you know, water like ourselves, that if they ever come in contact with something that's conductive. David, are you raising your hand?
Yeah, can I make an analogy?
Yeah, go for it.
It's kind of like potential energy with gravity. Think about it. Like a ball hovering above the ground. It wants to go back to the ground.
Yeah, if the ground, yeah, if the ground is more balanced than the air. Because sometimes the ground is saturated with electrons, and then what would happen actually is that the lightning would actually strike from the ground up, and that can also happen is that you can interact, like for example, say that you're interacting with a box of metal, and that box of metal has more electrons than you do. If you go to touch it, the arc is actually going to go from the box of metal to you. But if you were rubbing your feet on the ground and you had more electrons than it did, and then you went to touch it, then the electrons would jump and try to balance themselves out with the box and with you. So it's essentially whoever has more of a negative charge is where the direction that the energy is going to go. And so there's some really cool slow motion videos that we can see of lightning where the electrons will actually go up before the lightning comes down. And what ends up happening is that the electrons at ground potential are going up because that they see this relatively positive area sort of in the middle of the sky, but that all the way up above, up in the clouds, there's a lot more electrons, and so they sort of meet halfway. Is that first all of the electrons in the ground sort of creep up a little bit, and then the electrons up above also see that this sort of center area has less negative charge, and it will jump down below. And what ends up happening is that they meet halfway, and then all of the electrons that are in the clouds happen to notice that they overpower the electrons that are at the ground, and that they will continue. The lightning will essentially will continue all the way down to the ground. And so it's really cool. Like YouTube some slow motion lightning, but it's pretty nifty. And then if any of you have ever played around with a Van de Graaff generator, essentially it's just a piece of rubber that's just essentially rubbing up against a carpet, and that's essentially collecting a ton of electrons. And what happens is when you put your hand on this metal ball, all that's happening is it's essentially stealing all those electrons from the power source and from the carpet, and it's balancing it out with you. And so if you have your hand on it when you turn it on, then you'll just feel sort of weird, and your hair will stand up and all of that. But if you were to turn it on while you're not touching it, and then you went to go and touch it while it was running, it would give you a very nasty shock. That's why we try to be really careful whenever we pull one of these out, because it can hurt. It can hurt a bit, depending on. But one of the cool things too is that you could put your hand on it, turn it on, turn it off, remove your hand, and now you are charged, negatively charged. And now you could go, poke somebody, and all of the electrons that are in you are going to want to balance themselves out with whatever you touch. And so a little, it's a great prank. Just charge yourself up, and because the shoes that we wear are fairly insulated, it's not until you touch something that's conductive, like another person or a piece of metal, will any shock happen. And if we wait long enough, those electrons will sort of slough off those electrons, and will eventually balance out with our environment again. And so we see that with people who are working on power lines, is that they jump out of a helicopter onto a power line, work on the power line and fix it, and their charge is very different than what's on the ground. And if they were to essentially jump back in the helicopter and then go down to the ground, jumping in the helicopter in the first place, that would shock them to the point where that would probably kill them. And so what they do with the helicopter is they actually go out with a giant wire, and they touch the power line with the wire to the helicopter to balance out the charge. And then the helicopter will actually take its sweet time flying around until it lands on the ground to sort of help balance out the charge, where it's sloughing off some of those electrons while it's flying around. That eventually they dissipate. They go back into the environment. So that's static electricity. So pretty much the difference between static and current electricity that we consider is just the voltage. When we start talking about really high voltages, in the thousands of volts, we tend to sort of think of that more as static electricity, because that's sort of where it's practical. But we do have current electricity that does go into the thousands, but we tend to not talk about that in the practical sense. Okay, fun to poke the cat, tase the cat. All we're doing is we're balancing charge. Okay, let's talk about components. So if we just had electricity alone, that wouldn't be that wouldn't be really useful. And so what we do is we're able to essentially stick things or components or elements of whatever in the way of the electricity flowing, and that allows us to do useful things. So a component, which literally just means a part or element of a larger whole, and in this context, it's part of a machine or like a vehicle or something. And so all of these components have different uses. So we have this unpolarized capacitor here. This is for, this is just for generically holding charge no matter what the polarity is. So where the negative side, where the positive side, doesn't matter. Versus here, this polarized capacitor, this essentially you can think of it as a really temporary, very quick battery. If any of you have ever used a real camera, there's like that whining sound when it's charging up the flash, and that whining sound is that capacitor. You can actually hear the capacitor in the transformer, which that's the transformer, we'll talk about that, but you can actually hear this being charged up. And the reason we use a capacitor instead of just a normal battery is that capacitors are able to be charged and discharged very, very quickly. So they're very useful for that. Then we have diodes. Essentially, imagine a diode like a one-way pump. It only allows the electrons to flow one way. And then an LED is a light emitting diode. So it has the same properties of a diode, that it only allows the current to flow one direction through it. And what happens is that when the electricity flows through it, it also emits light as a sort of a side effect of the electricity passing through it. Then we have our octocouples. This is essentially a way of controlling whether or not you're allowing current to go through it or not, and you can essentially connect and disconnect it. Then you have your photoresistor. So let's actually talk about a resistor first. A resistor is essentially a way of limiting the current, imagine like if we're using the water pipe analogy, that it's a narrowing in the pipe, and so maybe some restricting baffles that will essentially prevent a ton of the water flowing through at a quick speed. And what it does is it converts that energy from electrical engineering to thermal, to heat. So resistors will heat up a little bit when you're using them. And so then a photoresistor, what it does is that, so a normal resistor is relatively constant in the amount of resistance that it offers. The more it heats up, that will change a little bit, but not really for our sake. A photoresistor, what it does is that it changes its resistance based on the amount of light that it is receiving. So say that you have some doors that open and close based on how cloudy it is, or how sunny it is for your house plants to get some sunlight, and you only want the doors to open up if there's sunlight. You can use a photoresistor to figure out how much light that you're receiving. And so then sort of along the same idea is that we have a very similar symbol to the photoresistor and the resistor, except it's got an arrow pointing at it. It's called a potentiometer or a pot. And what this is a resistor that you can essentially adjust. You can turn this giant dial, and that will change how much resistance it's offering. And if we were able to do our activity, which I'll talk about at the end, but we would have been able to play with one of these. And essentially, there's a few different ways that this is done. In some cases, what it is that it's just a round disc of resistant material. Maybe it's like graphite, like what's in a pencil, and then it's just got a little sweeper that essentially touches different points of it, and that changes the amount of resistance that it has. Then we have our relay. Just like the octocouple, it allows us to either connect or disconnect power or current from something. And then we've got our stepper motors. Oh, I need to not have my... we've got our stepper motors. And this is a motor that has lots of coils in it that allows us to sort of force it into particular positions. And then the bottom one, we've got our switch, which allows us to connect and disconnect things. Essentially, you can connect a switch and a relay together, and the switch could be for relatively low amounts of current, and then the relay could be for very high amounts of current. And so we do this a lot, hopefully, in like households that if you have a light switch, that the light switch could be really dinky and really small and really cheaply made, but that you have this very nice and expensive relay that's actually connecting or disconnecting the power. If you ever go into like a giant warehouse or a giant facility and you flip the lights, and then you have to like wait like a second or so, and then you hear like lots of chunk and like clicking noises, and then the lights all come on. That's because there are these relays that you flip a switch, and then that switch tells the relays to then connect all of the power. And so that's a very useful way of essentially being able to have these sort of cheap components or these low current components be able to control something that is much bigger and much more powerful. And then we have got our transistors. This is essentially what led to having computers, is that we essentially were able to take these transistors and make them smaller and smaller and smaller and smaller and smaller to the point where they're now nanometers. Or actually smaller, or microns, right? And this essentially allows us to be like a relay, but to be as fast as an electron. The issue with relays is that they take a noticeable amount of time. When you flip a switch, you can actually hear it click, and you can see that when things are off and when they're on, even though you've already flipped the switch. Relays actually mechanically have to move open or closed. Versus a transistor, it's literally just electron speed, which is practically light speed. So they make a lot more sense for computers than relays. A relay-based computer would be very, very slow. And then we have pictures of more switches. And then we have our a normal motor with a little fan blade attached to it. You might see this like on your fan. This is an alternating current motor. We've got light bulbs, right? These are components. We've got these coils and these transformers. So the transformers, everybody's got one. Anyone that's got any kind of charger for their phone, right? They've got to convert the wall power from 110 volts alternating current to something that your phone or your digital device can consume, which typically is about 5.5 volts DC. So this transformer is able to not only convert the voltage, it's able to drop the voltage or raise the voltage, but it's also able to change the AC and DC and have that rectified. And the way that it can do that either with the coil windings that are in it, or it can use that with a pair of diodes here that are inside of it to essentially allow it to convert everything to DC. So transformers are very, very useful. We would be in a lot of trouble if we didn't have them. And they're fairly efficient. And the cool thing is that they can make things go, they can raise the voltage or they could drop the voltage. So for example, your microwave has a few transformers in it. It's got a transformer that takes the 110 and pumps it up to a few thousand volts to microwave levels. Yeah, so those components, and essentially what we do for making electronics or making things that are useful is that we take all of these electronics and we sort of mix them and connect them in different ways to change their behaviors. And that's all, you know, the difference between a laptop and a cell phone and the light that you have at home is that you're taking all these components and you're arranging them in a way that makes them useful, right? If you just had a switch connected, if you just had a switch that was connected to power, that wouldn't be particularly useful, right? You poke the switch and the switch gets really hot and it catches on fire. But maybe if you connected that switch was then connected to a light bulb, now you have something that's relatively useful, right? You walk in your bedroom, you flip the switch and then a light turns on. That would be considered useful. So taking all of these components and connecting them and arranging them in a way that does what you want them to do is part of electrical engineering. Okay, so I talked about resistors and the different kinds of resistors, but let's actually talk about like what makes something a resistor.
Did you just cut out?
Yeah, we can't hear your audio.
Sorry, everyone. My network seemed to have dropped out.
It's all good.
Okay, let's try that again. There we go. Okay. Yeah. So the things that make these materials really expensive is not only because they're really pretty and that they're fairly malleable and easy to work with, but also because they're conductive. And we see that their use is increasing the more and more we use electronics. And so, yeah, so good conductors, and there's a balancing act that we have to do. Like it would be great if our power lines were all made out of gold. If we had enough gold to make that possible, that would be fantastic. But it's not really practical. We don't have enough gold on this planet. We've got asteroids that are in orbit of Earth that we could bring down and utilize to do that. But right now, what's on this planet, we don't really have enough to just practically make everything out of gold. And so we have to make compromises. And the power company does this all the time. So for example, most of our power lines that are outside are aluminum. They're sort of, they're conductive, they're okay, but they're nowhere near as good as gold. But you're not, if somebody strips the power lines off the power lines that are in front of your house, they're not going to make a ton of money off of it. So people don't really go around stealing power lines. Versus what you do see a lot is that people go into people's houses and they strip all the wiring out of the houses because most of the wiring in houses is hopefully copper. And copper is much more conductive and is much more valuable. And so we sort of see this trend, and actually silver should be moved down, but we see this trend that from aluminum to copper to silver to gold, that the more valuable it is, that sort of the more useful it is in electronics, because it's more conductive. And what ends up happening is that the less conductive you get, so like aluminum, what it ends up doing is that it converts any energy that's sort of lost in the transmission going from the power station to your house, that tends to be converted into to heat. And so the worse and worse you get, so like a resistor is sort of in this middle zone where it essentially is taking that energy that's lost between one spot and another spot, and it converts it to heat. And in the case of resistors, we're intentionally doing that. We're intentionally trying to have the current from one side to the other side be less. And so sometimes that's by design. The materials that we choose is by design. Maybe we don't want as much current from a power source, or maybe we want as much power as possible and we don't care about what the price is, and we use gold. Things maybe that we have a hard time accessing, or that we don't want, or that we're not able to interact with, or we don't want to interact with, we'll use gold. So you see a lot of gold usage on satellites and on rovers, things that we don't have access to because we want to have the best quality. And what happens too is that when things heat up, like the aluminum, when you lose energy to heat, when heat's a premium, and energy is a premium in space, so you don't want to lose any kind of, you want to reduce the amount of energy you're losing. But also what happens is when things get heated up, they cause lots of microfractures, and that will eventually cause them to stop working. So if you use gold, you're actually more likely to have something last longer because it's not heating up and cooling down all the time. So there's this compromise that you have to make when you're selecting the material, is that how much money do you want to spend for what you're doing? And I mean, for power lines, we don't really care because those get replaced every once in a while, and that maybe losing a ton of energy is perfectly fine because we're able to build more power plants fairly rapidly versus a rover that's on another planet. We can't go and give it more energy. We can't add, attach another solar panel to it. So it's very important that the amount of reduction of performance is reduced as much as possible. Okay, so pencils use graphite, which is sort of in the middle of the zone. So you can essentially use a pencil as a resistor. So there's a great exercise that we've done where you essentially are able to draw circuitry on a piece of paper and connect alligator clips to it and actually power up circuits with pencils. And you can actually buy pencils that are even more conductive, that have particles of these materials, of aluminum, silver, or gold in them to make them even more conductive. And then we have things that we call insulators, which we consider not to be conductive really at all. Or that you have to go to some insane voltages to make them conductive. And essentially what happens is that the lower the voltage, I forgot to mention that, the lower the voltage, the better off you're going to be at being able to get that voltage from one side to the other side of whatever circuit or whatever you're working with. And the higher voltage, essentially, like you can electrify a table. If you go into the 30,000 volts, you can actually take like the surface of a table and electrify it. The thing though is that the current is going to be very, very low. So it's going to shock you if you went to touch the table, but it's not going to hurt, and it's not going to really, it's not going to hurt too bad, and it's not going to be able to do any kind of damage. So essentially insulators we can think of as things that are really not good conductors, things that don't really allow electricity to travel well through them, and that they can't really store electricity at all very well. And we also have glass in this field, is that we use glass as a really good insulator. But like wood, for example, or cardboard, if we expose it to water, that sort of moves it more in the direction of being a conductor. And if we add it to, and if we put salt water on it, then it becomes even more of a conductor because suspending salt in water makes it more of a conductor. So yeah, for practical sense, we consider conductors these nice, very expensive metals. And for insulators, we think of things that are non-metallic, rubber and plastics. Okie dokie. All right. Okay, so circuits. So you could just think of it like the lights in your house. That if you turn the light on, then you have a closed loop. That things are continuous. That the electricity is able to flow through, just like the water pipe analogy. But if you open it, if you turn it off, if you open it, then you have this sort of gap where you have this open air in it, where the circuit doesn't work and the light's off. It's only when the electrons flow. It's only when the electrons flow do we actually get energy or electricity through the light bulb, because all electrons are just hanging out in the light bulb, but they need to move in order to actually light up. And so a closed circuit will do that. A closed circuit will allow the electrons to flow through the light bulb, whereas an open has a sort of gap of air, and that prevents the electricity from flowing. So yeah, you can think of it just like water. A lot of people use the water analogy. And so here's an example. This is an open switch. The switch is physically open. And so will this light up? Right. No, David's right. So yeah, this will not light up because the electrons are not able to flow. The electrons are essentially stuck here. They're not able to get to the other side of the battery. But if we close this switch, then the electrons are able to get to the other side of the battery, and then it lights up. And so we have different ways of organizing components. And so the two primary types that we organize components in a circuit is series and parallel. And you can think of this exactly like we think of like books or TV series or whatnot, or comics or whatever. Is series is one thing after another. So this is in series, right? It from the battery goes the resistor, goes the LED, goes to the switch, goes to the battery. And so series means one after another. Versus parallel, this is not a parallel circuit. Parallel is all at the same time, right? Like parallel universes or whatnot that we use in the comic books, is that those are all happening at the same time, independent of each other. And so we can see this in this picture, right? Here we have series, it's one light bulb after another, versus parallel, where this side is connected to the same spot to the battery as this guy too. Cool. So we got parallel is all simultaneous. Yeah, what's up?
I just want to. I mean, basically, in the go to the last slide.
Yeah.
I feel like it would be better if. It would be better for all of us if you explain how the resistors work. I mean, I'm a computer engineer, so I kind of know this, but you explain how it would affect the LED. Like
yeah.
In a way.
Yeah. So okay. So the reason why we put these resistors here is that maybe this battery, the voltage of this battery or the current of this battery is much higher than what this LED can handle. And if you just plug this LED directly into the battery, it would burn up. It would get very, very hot, and depending on how different that was, it might even shoot out of the socket. And so one of the things that we do to solve that problem is that we stick in this resistor that essentially allows us to limit the current and limit the voltage so that the battery and that the LED are able to play together properly. Yeah, so typically what you do a lot of the times is that then there's lots of charts and diagrams and there's actually when you buy an LED, a lot of the packaging on it actually says, hey, if you're using this voltage battery, use this kind of resistor, this ohm resistor, and that you want to pair those up, because otherwise, if you have a resistor that offers too much resistance, then the LED is going to be very, very dim, or you're not going to be able to see it at all. Versus if the resistor is not offering enough resistance, then the LED is going to burn up very quickly. Is that good?
Yeah, I just wanted to help explain the class.
Also, the echo's kind of distracting me trying to talk.
If I kind of hear myself,
Yeah, sorry. Well, I can mute when I can mute when you're talking, but yeah, I have to like have to hit a button. Okay. Yeah. So resistors are a useful way of making things play together nicely. Or if you just want to generate heat, like your toaster, all your toaster is a giant resistor and a switch. When you push the switch down on the toaster, it's just these giant resistors that they heat up and make your toast. They're wonderful things. Okay. Yeah. So we've got our series and we've got our parallel. And so on our phone, right, we're able to, on a phone or a more complex thing, we're essentially able to sort of mix and mosh things in series and in parallel to be able to diversify what they're doing. In this example, we're just using LEDs, but imagine that maybe you stick a switch right here on this guy, and so this light is always on, but that the switch here is able to turn it on and off. So this light is able to turn on and off, but this light is unaffected by putting a switch right here. Yeah, so you can essentially mix components in forms of series and in parallel together to make modern circuitry. And yeah, just to re-emphasize this, it's closed, there's no air gap between them, and that allows electrons to flow, lights up the LED. If it's open, then there's this air gap here, and electrons aren't able to flow, and the LED is off. So this is one of the activities that we would have been doing. Essentially what we do is we make our own circuitry using tinfoil, make little shreds of tinfoil, and we essentially lay out the battery and these pipette tips and the tinfoil and the light, and we use the cardboard to make a little switch. The cardboard's wrapped in the tinfoil, and we're able to make a little cute little circuit. So yeah, we're not going to do that. Okay. So that's it for electrical engineering, right? This is all old slides. We are not making squishy circuits. Okay. Any questions about electrical engineering before we move on to the next topic? Let me open up the chat window because it got closed. Okay, so looks good. Okay, so let's move on. Let's do computer stuff. Okay. Oh, that is an old email. Okay. Yeah. So this is my moneymaker. Computer science, computer information, and computer engineering. This is where people actually pay me to talk and do things and think about things. And these three fields are distinctly separate from each other. And that's actually a very large problem, is a lot of times they don't talk to each other. And so one of them might have the solution that the other one thinks that is, something is totally impossible. And if they were just to talk to each other, that wouldn't be an issue. So actually, I was at a cybersecurity conference 3 years ago, where I was at a booth and they were doing a demo, and I asked them a question about, how could you use your product? Do you offer this product in this form? And they were like, oh no, that's not possible. You can't do that. That would be really great though, because we could make a ton of money. And I'm like, the booth that's 10 feet across, like literally across the aisle, that's what they do. Like that's the solution that they offer. Like that would be that piece of the puzzle. And I literally grabbed the engineer's hand and walked them over to the other booth and was like, you two talk about your products. And I mean, they had the whole week, they had literally been 10 feet away from each other, thinking that, their product was only useful in this really niche environment. And that if they interacted with each other, they could suddenly expand both of their product offerings in a huge way that could make them tons of money. And it was just the fact that they just didn't know that problem had already been solved by the other person. So yeah, communication is really, really key no matter where you are, but like you see that a lot in the computer world, that the science, information, and engineering, and there's some resentment too that you might come upon people that people might say, oh well, that field they do it that way, and you know and that's wrong because I was taught this way, and sort of just put that all aside. Don't spend too much time on that. Okay, so from phones to computers to medicine, technology touches every part of our lives. If you can create technology, you can change the world. This is Susan, CEO of YouTube. Actually, I think she's moved up from there. This is a fairly old slide, but yeah, I mean the idea being is that if we can build things, even if it's not even writing programs for computers, but if we can build things, we can affect other people's lives, and hopefully for the better. So let me give you guys a little bit of a history lesson so that we can really get an appreciation for where we're at. The first person I'd like to talk about is Ada Lovelace. She's regarded as the first computer programmer because she wrote some of the first algorithms for machines. And this was before machines could really change their behavior. And so she essentially wrote out this language that you could essentially, given an input like moving a lever, you could change the behavior of a machine. And that was a very novel idea, right? That we were able to walk up to something and hit a different button or something, and that based on whatever button or input that we give it, is going to change the behavior of whatever we're using, which was a novel idea that we really take for granted, and so we can thank Ada for that. The next person that I like to talk about is Grace Mariah Hopper. She's a total badass. So she invented the first compiler, and I'll show you what the significance of that in the next slide. But that essentially allows us to take things that are relatively human readable, and I see boos from David. What's up, David?
I was just booing Susan Wojcicki.
Oh, okay.
We say her last name.
Okay, so Grace essentially made this machine-independent programming, which allows us to write something that is somewhat human readable, and it converts it to something that the computer, that specifically the processor, is able to understand. But it also allows us to, or that's a compiler. The machine-independent programming allows us to write a program once, and that it runs on multiple different kinds of systems. And we can see that problem in one of the most badass things that I think she did, besides the previous two, was that she was the first programmer of the Harvard Mark I computer. What happened was that the military had built this multi-million, if not billion-dollar, I think due to inflation, it's now billion-dollar computer. It was it was massive, multiple stories, big, and they built this thing to look at missile trajectories, but no one could figure out how to make it do anything besides basic addition. And so they brought Grace in, and she was able to essentially write all of the code to be able to make it calculate missile trajectories. And that was sort of illustrating the problem that one program that she wrote would not work on an almost identical computer that was next door. The computers were sort of custom built at the time, and they were very large, and that just the manufacturing differences between making it in this building versus this building was enough that the same program wouldn't work. And so that led to the development, her developing the idea of being able to have machine independent programming, that you could program something once and that it would work on multiple different kinds of systems. We take this for granted, right? We download an app on our phone, and the app was developed by somebody with a totally different screen size, or maybe they didn't even have a real phone when they were testing their program. So being able to write something once and it running on multiple different environments with lots of different kinds of hardware, we can really attribute that to Grace. And there have been a lot of other people who've contributed to that, but that she was the pioneer of that concept. Okay, so let's just get number bases out of the way. We're all familiar with the decimal system, hopefully, that this first, where's my pointer? Here we go. That this first column here is hopefully how we count, right? How we're accustomed to account. But computers use binary, right? They store traditionally, classical computers store everything as ones and zeros in some way or another, and that's also how they make pretty much all their decisions. Is either something as 1 or as 0, and that's base 2. Base, if we recall from our algebra class, base is the number of digits or number of values per digit that we can express. So in base 10, in one number place, we can express everywhere from 0 to 9, which is 10 distinct things. But in binary, which is base 2, hopefully the my pictures aren't in the way, but base 2, we only can express 2 different things, a 0 and a 1. And the moment we run out of things to express in that digit spot, we have to essentially go up 1. So this becomes 1 and this becomes 0. And we say the same thing in base 10, right? When we hit 9, if I add 1 to 9, we run out of numbers that we can express. So the first digit spot goes back to 0, and then we carry a 1 over. So it's exactly the same in base 2, except it just happens much more rapidly because we can only express 2 things per a digit. And one of the things that we do is that binary is really, really hard to look at over extended amounts of time. I mean, I've literally spent days and days and days where, like, on a project where a single bit had flipped somewhere and having to look at tons and tons of data, and binary gets really, really old. And so what we're able to do is we're able to convert that base 2 into base 16. And the reason being is that the smallest value in binary is 0, right? Hopefully 0 is common. But then in 4 bits or 4 digits in binary, we're able to express that as 1 digit in base 16. There's this nice relation with powers of 2, right? That 16 is a power of 2. And so we're able to express the maximum of 4 bits with 1 digit in base 16. And so looking at this base 16, or hex as we call it, is much, much easier for our human eyeballs. And I'll show you an example in the next slide of that. And then just as a side note, there are, the Russians try to build a trinary computer that it could be -1, 0, and 1 during the Cold War. It didn't work out too well with them because all of their computer scientists used traditional computers. They only understood base 2. And so that was, of course, abandoned. But that was an attempt to try to make a computer that you couldn't easily break. Okay, so let's look at some what a compiler does. And so these are compilers and examples of environments. So not all of these necessarily use a compiler, but it's the same concept. We take something that's relatively human readable, echo hello world, and this is, so in Bash, echo hello world, C++, cout hello world, Perl, I need to update this, Perl, hello world, and I'm missing my closing quote, sorry about that. Python, we have print hello world, and then Java, we have our system.out.print hello world. So all of these are human readable. And what happens is that a compiler takes, like, for example, this line right here, this is what I did. This line here gets converted into this right here. This is an assembly. I wrote this myself, and it works. You can trust me. So this line here, cout hello world, gets converted to this right here. And this is in hex. And the reason that we express this as hex is because if we took this one, oh, my cursor's in the way. If we took this first four digits in hex, and we convert it to binary, we would see what we have down there at the bottom. And so just this, I guess, paragraph of hex, if we were to convert it all to binary, would be about 3 pages, like solid pages of ones and zeros. Yeah, what's up, David?
The first word, you mean the last word. Or the first word in sequence, I mean.
Yeah.
16 bits.
Yeah. We could say word. Word would be, let's see, 8 bits, 4. Yeah, there we go.
16 bits.
Yeah, well, I'm adding, making sure. Okay, but also we could say 4. We could say 4 digits as well, because everyone knows what the word digits mean, hopefully. Okay, yeah. So we would end up with 3 pages, and that's really, really hard to look at if, for example, one of the bits had flipped, right? A bit had flipped, and that would change this 16 or this 6 here to a 5 or a 4. And so if you're looking for a single bit was flipped, which I was, that's all I cared about. I didn't care about the data. I was just comparing it and doing a diff. But I needed to, the program told me, yes, there's a difference and it's here, but then I had to figure out in what context and where it was and what the ramifications were. Being able to visually inspect it with your eyeballs, hex is much easier to see. If I gave you this paragraph and then an identical one, that you could pretty quickly, within about a minute, find a bit that was flipped somewhere. Whereas if I gave you 3 pages of binary of just ones and zeros and said, hey, figure out if this 3 pages and this 3 pages, find me where that bit flipped, that would take you a very long time. Yeah, what's up?
Can I show the class what flipping a bit might look like? Specifically
in that word you
express at the
bottom of the page.
Yeah, sure. You wanna take over the share?
Yeah.
Go for it.
Here it is. Okay. So you had 614E at the front. And let's say you accidentally flip this bit right here. So if that's affecting the 4, where's the pointer? Well, that's affecting the 4. I'll just highlight it. So if I do that, you'll see that a random bit flipped, and that just changed to a 6. Because if you want to go ahead and explain that, like how this happens here.
So these are all powers of 2. So essentially, if we take the chunk of those 4. These are all powers of 2 that are all added to each other. So the first one is 2 to the 0th, which is 1.
Mm-hmm.
Then the next one is 2 to the 1st, which is 2. Then the next one is 2 to the 2nd, which is 4. And the next one is 2 to the 3rd. And all you're doing is you're adding up all of those values together.
Right.
And so if you changed the first one, if you change the first bit, if the first bit got flipped, then you would only see a value change of plus or minus 1, depending on which direction you're looking at the bit flip. Versus if it was the second digit.
So something like this, where it was, you have basically all of this is to the power of 2. Wait, I'm sorry.
No.
It would be my bad.
Yeah, that's not right.
Yeah, no. I'm messing up. Go ahead, take control.
Okay.
Let's see. I feel like I want to visualize it, but I'm messing.
Yeah. So I
can starting from 0.
I could type it up.
2, 3, and then to the base of 2 from that. As
other way. Flip them. So it's 2 to the it would be.
Oh, my bad. Yeah. From here.
2 to the 1st.
Yeah. Okay. I'm done. I'm not a teacher. Sorry for trying to take over the course.
It's all good.
Go ahead.
His chart before with the binary chart would be helpful for that.
Yes.
Well, yeah, I got a lot of material to jump through, so
yeah,
let's just boogie woogie. But yeah, so the idea being is that per spot, yeah, per spot in it. Here, these are just powers of 2. Everything's a power of 2. Just remember that when you're working with computers. Okay, so yeah, so what happens is that the compiler converts these things that are human readable into things that are understood by the computer, and specifically the processor is able to interpret these. But in the sense of the environments, like if we're working with Java, there's actually a virtual machine that sort of has its own fake processor, and that the virtual machine has code that's written like this, but that the code that we write when we compile it, and that's in air quotes, that converts it to something that the virtual machine understands. Yeah. So okay. So that hopefully that gives us an appreciation for, we don't have to write this stuff anymore because we have compilers. If you look at this stuff and you really like this stuff and you want to write compilers yourself, there's a lot of money in it for you. But I mean, I hate it. It's incredibly dull work. I just am very appreciative that somebody else before me has solved this problem, but that I have enough knowledge of this to get myself into trouble. Okay, yeah, and this is what computers used to look like. They were thousands and thousands of dollars, and they didn't really do too much. And in order to code those ones and zeros, in order to code these binary ones and zeros, you physically had to put holes in pieces of paper. And God help you, you made a mistake and you put a hole somewhere that you shouldn't have put a hole. Now you've got to either like tape up the spot and punch a new hole, or you've got to start all from scratch. Or if the machine that you're feeding into, it actually munged up and messed up on your cards, now you have to figure out what kind of code was on that card, and you've got to recreate it. And that can suck. So like a lot of people would have boxes and boxes and boxes of these punch cards. And so there was actually a programming language called Lisp that if you could, or was it Lisp or was it? Oh, no. There was an attachment to COBOL that you could, as long as you had the first punch card was correct, that you could feed in any of the subsequent cards in any order. And that was considered like revolutionary, that the cards themselves would know, they would have an ID on them so that when you loaded them in, because a card is a set size, you knew how much memory to reserve in RAM per card. And so the first card you'd load in would tell you how much memory was needed, and then as you were feeding in each card, it knew where in memory to load that particular card. And that was really nifty and really cool. Nowadays we don't really have to consider that, but we actually see this as a vestigial structure, like a leftover structure, whenever we're looking at editors, like text editors, and we actually look at line numbers in those editors. There's actually an expanded view for the line number, and you'll notice that between the lines there'll be a significant gap in the addresses that are used in the lines, and that's because they're actually leaving a full punch card of memory addresses between each line of code that you write. We also see this on GitHub. That's a collaborative way of developing code, is that literally some of the stuff from these punch cards, the way that we organize memory and that we do handle our editors, is still left over that's totally not necessary. Yeah, okay. So another activity that we would have done but we're not going to be doing is this ASCII activity. And essentially here's just a few letters, the lowercase letters in ASCII. ASCII is essentially a way of storing and transmitting messages. And ASCII was originally made for teletypes, which are essentially typewriters that are connected to each other or connected to servers that you can essentially type on the keyboard or type on the typewriter, and that it would send that signal to whatever you're talking to. And ASCII worked both ways. So what would happen is that when you would have a screen or a typewriter, when the server would send you data back, or another one of these typewriters would send data to you, they would essentially send you a message on another line using the same ASCII. And so the ASCII actually we still use it today, and it has all kinds of extra stuff that only has to do with the typewriter. Like there's a carriage return. If you ever used a typewriter, You know, like when you sweep the top part and it goes ding, right? That the carriage return. There's both the carriage return, that physical mechanical operation, but also that bell sound is actually still in the ASCII standard today. So there's a lot of sort of leftover stuff from back then, and it's a fun prank to play on somebody. Is that you have them open a file that, or you send them data that has that bell character, and for some reason their computer makes a beeping noise, or the screen flashes, or however the bell is handled. It's always an excellent prank. But essentially, this would be, I would play a metronome, it would go ticking, and then I would have handed you a bit, and you would have flipped the bits back and forth, and you would have transmitted messages across, and it would have been terribly slow, and a lot of giggling would have happened. And then I would have said something along the lines of, yeah, the Wi-Fi that your phone's connected to right now is 4 billion times faster than the metronome that we were sending, and that's how we can send text messages. Something along those lines.
So
Okay.
on that chart, A is like 6. It's like 6-1. Is that right? Why does it start at 6-1?
So this isn't 6-1. So this is so if we ignore the first 3 bits, this is just 1. But this here, if we keep in mind, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So that's 2 to the 5 plus 2 to the 6 plus 1.
Oh, I was reading it as 2 numbers. You're saying that's all one number.
Yeah, it's all 1. Typically, you see this a lot where you leave a gap between 4 bits. That makes it easier to read.
All right.
Yeah, that's a pretty common strategy. Yeah, and so if we notice that all of these have the same first 3 bits, right? And what you do to make it uppercase and lowercase is if you change this 1, you change this 3rd bit, and you make it a 0, and now it becomes uppercase. And it's sort of weird, actually, that the lowercase is a higher value, but that's just how ASCII works. It's because originally the typewriters for ASCII had a smaller address space. They didn't have these first 3 bits at all. And the typewriters were only uppercase. And so what happened is when they added this bit, they added this extra bit, they're like, cool, now we can do uppercase and lowercase. And then they added this bit and then this bit, and then suddenly we could do more and more and more. And so now when we look at Unicode for emojis, emojis are literally stored in the same way, but they use double the amount of bits. They use so yeah. There's UTF-8 or UTF-16. So yeah. So the Unicode consortium, they essentially use more and more bits, and that allows us to have emojis and bananas and airplanes and all kinds of things like that. And all we did was kept adding more and more bits to be able to express more and more things. And we leave all the old stuff behind. Okay, so yeah, that's ASCII, or some of ASCII, and you can always look up ASCII table if you're really curious at how that works and how we store those things. And then if you want to know about emojis, you can look at the Unicode consortium, and they're always adding more and more stuff. And so we actually run out of spots to be able to express it, and they keep essentially adding more and more bits, which is why our text messages with the same messages get slower and slower and slower, and why we have to buy newer and newer computers and newer and newer phones, because we're transmitting even more. Even for the normal letters, is that we have to pad these. We have to stick a ton of zeros in front of them so that they're compatible with the newer eggplants and whatnot. Okay, I think this is, yeah, last 2. All right, so last 2 people I like talking about is Anita Borg. So she worked at Xerox PARC. She was a chief researcher. And so she actually was the chief researcher for Ethernet, which is the protocol that we use to essentially connect all of our devices to the internet today, and how we connect them all together. That's also, Ethernet is also the name for the cable that we physically use to plug in internet to our to our computers. But Ethernet is also the protocol, the actual language that we talk over the air or over the wire. And she also was the chief researcher for the mouse, which we take for granted nowadays, but that's really important, having a pointer device. And even though we think of Xerox as some kind of copier company, they actually made the first real like desktop computer with a mouse and a keyboard and internet connection. They were way ahead of their time. And Microsoft essentially bought all the rights to that. And Steve Jobs happened to be sneaking around during that time, and he essentially stole all of those ideas and didn't pay a dime for any of that. And so everyone says, "Oh, it's Steve Jobs, the revolutionary." No, he just stole a ton of ideas that Microsoft paid Xerox for because Xerox didn't think that it was useful. Okay, enough of that. Anita Borg also invented a fault-tolerant Unix-based operating system. Originally, what happened was that when you were running a program, and if you made a mistake in your program, you would take down the whole computer. And that could actually result in physical damage to the computer, or it could result in just a lot of downtime. Like the computer was physically stopped working until somebody had turned it off, cleaned up the memory, powered it all back on, reloaded the operating system, reloaded all of the software necessary to operate. And that sucked because that happened a lot, especially with like student servers that students could, or timeshares that students could access. They could run whatever code that they wanted. And typically student code would break it, and it would take the system down for several hours, even if somebody was right there and was notified immediately when the system was taken down. It would take them quite a bit of time to get the system running again. So we can thank Anita for the idea of a fault-tolerant Unix-based operating system, that a bad program could go awry and essentially the operating system would kill the program before the program could take down the whole system. That's why we're able to run really crappy applications on our phones and our computers, and maybe the program crashes, but hopefully the program doesn't take out the computer. She also developed the mass emailing systems. Originally, emailing was strictly one person to one person. So the idea that I could have a newsletter that I could send out to everyone saying, "Hey, there's this virus going around. You should probably stay at home." We can blame Anita for that. But then, being able to, from one person to be able to send to multiple people and have group emails is very useful. Imagine if you had a group email and you had to compose a separate email to each individual person. That would take quite a while. So we can thank Anita for that. She also founded the Institute for Women in Technology. So that's Anita Borg. Very thankful for her contributions. And then the last person I'd like to talk about, the most sort of engineering person out of all of this, is Margaret Hamilton. She's still, sorry about that. She's still with us. So she was the lead developer for the Apollo flight software. And this picture here is her handwritten, her and her team's handwritten code. All code was handwritten, no mistakes. And you can see it's a little bit taller than she is. And I mean, I was watching, there's a guy called Curious Mark that he had found one of these books, and that they were spending enormous amounts of time trying to look through it, and were amazed at the fact that people had handwritten all of this code and that it was absolutely impeccable. And really, it was her foresight for errors, the idea of what could go wrong, what sensor could break, what kind of erroneous data could we receive, and how should we handle that, that I have huge respect for, because I see a lot of code out there that people write that they never stop to think of what happens if things are not optimal, if anything extra happens. If you're an engineer and you're building a bridge and you design the bridge so that it's totally robust, you could drop a tank on it, no problem. But the moment that somebody pulls out a single bolt, the whole thing collapses. That's not a good bridge. So it's really, really important that you always look at whenever you're designing anything of how could it be, you know, accidentally misused or maliciously misused, and to make sure that whatever system that you build is very robust to that. And so, you know, Margaret here, that was really, that was her. That's what she brought to the team, to her team, was that foresight of errors and making sure that people were writing good code that could hold up to things failing. And really, she's the reason why we landed on the moon multiple times, was that things could go wrong and that there was a way to handle those things going wrong. Before that, she actually wrote all of Project SAGE, which was originally for detecting missiles being launched. We now have other ways of doing that. But now, Project SAGE, this code that she wrote 50 years ago, is still in use. That's actually how we do pretty much all of our weather predictions, is we're still running her software to do that, is looking at satellite imagery to determine, you know, clouds and likeliness of weather events. But she wrote that actually to detect missiles being launched. So it's amazing that, you know, the code that's that old is incredibly still useful, and that any kind of errors that you might get in the, you know, in the weatherman's predictions, you know, keep in mind that that code is 50 years old. Okay. All right. Yeah. Any questions about those individuals, about these historical individuals? You can be very thankful for their contributions. Okay, let me pull this up. I'll just stick it over here. Over that one. Okay. All right. Let's talk about bits. So we talked about the normal bits, the classical bits, right, where we have a 1 or a 0. But we live in excellent times. We live in this quantum reality where we see, you know, thousands and thousands of quantum computers popping up all over the place. Google's got thousands, the government's got thousands, Microsoft's got thousands, Amazon's got thousands of these things, IBM's making thousands of these. I mean, everybody's got to have a quantum computer or be making a quantum computer. And the reason why is I mean, it's a bit complicated, but hopefully this slide will help clear that up. So the first quantum bit that we have that we really don't hear about ever is called a p-bit. And a p-bit is everything between 0 and 1, including 0 and 1. And so let's see how many people remember algebra or math. How many values are between 0 and 1?
Infinite.
An infinite amount of values. So wouldn't you think that the physicists would be satisfied? They have found this bit that can store an infinite amount of data, right? Wouldn't that be pretty sweet? Well, the physicists were not satisfied, and they kept going. They wanted more infinity, because such a thing is possible. And so this is the thing that we hear about all the time, is these qubits. And so a qubit is not just between 0 and 1. Now a qubit is essentially a point anywhere. So yeah, essentially imagine a point anywhere on the sphere. So we got polar coordinates, and then we've got any distance from that center. And then imagine that that point is actually not a point, it's a vector. The point is the base of the vector, and it's a direction vector that goes anywhere along that sphere. And so we have something more like the lines of, 8 infinity, which last time I checked is still infinity. And so these are these qubits. This even more data that we can express. I mean, imagine that you have a qubit and it stores all of the music ever, and you're able to share that qubit with somebody else. That would be pretty nifty, right? You suddenly wouldn't need to have that stack of iPods anymore. You could just share a qubit around with everyone. And this is where we hit an engineering problem. Qubits are not stable. The reason they're not stable is because we have inferior refrigeration technology. We actually need all those HVAC engineers who actually understand heating and cooling to solve this problem. So qubits, even with modern technology, a qubit is only stable for about 4 to 5 hours. So you could put all of this information in a qubit and keep it very chilled and very cool, and then that's all gone in a few hours. So that's unfortunate. So we need somebody to solve that problem for us. So I'm looking at all you guys and gals and whatever identity that you choose to identify as. Okay, so yeah, so qubits are a really nifty way of storing an enormous amount of data, but they're not stable, and that's a problem. Another really cool thing about qubits is that you can quantum entangle them. I know everybody's brains hurt. My brain hurts too. But you can essentially take two qubits and you can connect them in a way that if one of them gets altered, the other one will also be altered. And so you can now stick them in different locations. So for example, we have a satellite in orbit that has one of these qubits that was entangled, and that they were able to essentially, it was a photon qubit, and they were able to essentially turn it on and off, and that they were able to see the one that was down here was affected by that being turned on and off, and vice versa. So that's pretty nifty, because now imagine that you have a radio that can transmit an infinite amount of data in essentially no time. I don't think we're bound by the speed limit of light with quantum mechanics. And so now imagine that you have some people who got stuck in a cave and they have a radio that is able to transmit through all of that rock that a normal radio wouldn't transmit through. Or you were on Mars and you were really, really far away and you needed to transmit lots of data back and forth. If we could entangle these qubits and then make them stable so that they could last a while, that would be pretty nifty. So hopefully we see that within our lifetime. But yeah, just make your brains flex a little bit. So that's bits. Any questions about bits? All right. Okay. Moving on. All right. Let's talk about the different fields, because they are different. So the first field that we talk about is computer science, and they're sort of the most useless in the groupings of them. These are people who are taking things that were already built by electrical engineers and computer engineers and making them do things. So they're taking hardware, and essentially taking all these symbols that the computer understands, or maybe that they understand, converts it into something that the computer understands, makes the computer or the electronics or whatever it is do something useful. So pretty much all computer scientists is doing all day, every day, is writing symbols that the computer can understand that makes it do things. They're not building anything, they're just making it be useful. And this is my main moneymaker, which is why I'm able to just sort of bash it. But it's a very useful thing. It's very sexy. They're always hiring people to be computer scientists. But in the sense that what you're physically doing is just flipping some bits on a computer, and suddenly it does useful things now. Versus computer information, which let's just pull this guy up. So computer information is a little bit different. Computer information is more looking at the organization of how things are connected and making high-level decisions on what computer is connected to what computer, and how do we fix this computer relative to this one? Do we add a C drive to solve this problem? These sort of higher level things. And so under the umbrella of computer information is computer security, which is where I've worked for about 10 years. I worked in that field, and I'll probably go back to that after I finish up my degrees. And so computer security is a much different field, because we're looking at how do we make things robust? How do we write code or enforce people to write code that's good, that's not going to have vulnerabilities in it? And then also, how do we prevent malicious people from doing damage? And so right here, we're looking at an attack map. These are attacks, these are cyber attacks that are happening right now as we speak. And you notice that there's a lot of activity, going to specific spots. We see a lot of activity at Silicon Valley. We see a lot of activity hitting the New York, DC area, right? Because these are hot spots. These are spots that people either want to steal information, or they want things to stop things from working, or whatnot. That there's intent behind these attacks, whether it's they just want to devalue somebody's stock because their website doesn't work, or if they want to steal information from their site, like people's credit card numbers or whatnot. There's always intent behind these kinds of attacks that's going on. And this is very real, right? We're not firing missiles at another country or anything anymore. We are sending cyber attacks. We are sending these payloads. We're sending these payloads over to other countries to try to destabilize them, to prevent them from doing whatever we want to prevent them from doing, and vice versa. They're doing the same. And this is not very well regulated, as you can see all of these attacks, right? The amount of people being punished for doing, for doing these actions is very, very limited, because a lot of times people are doing these under the umbrella of their country, and their country is not going to just give them up to whoever they're attacking because they're doing it for their country. So yeah, this is very real. This is happening all the time. That we're being attacked, and this is what war looks like now. Because imagine I'm able to send a single data packet over to an industrial control system that controls the water pipe for your town or your city, and I'm able to pulse it at a specific frequency that I know the gauge of your water pipe, and I'm able to cause your water pipes to explode or your gas lines to explode by sending a single packet. I didn't need to send a bomb or fire a missile. I'm able to send data over to something that causes physical damage. We see all these people with all of these internet connected pacemakers and insulin pumps. Imagine that a single one of these little dots that's flying by, that's what it's doing. It's killing somebody. It's stopping their heart. So we have to think about this when we're building something, is that there are malicious people out there, and we need to build things to be robust, and we need to be mindful that there are always bad actors out there. Fortunately, there are a lot more good actors than bad actors, and so we're able to build things that are very robust. But constant vigilance is really, really important, and I can't illustrate that enough. And so yeah, this is the world that I live in, is looking at these kinds of attacks and trying to mitigate them, trying to reduce the amount of damage that they're able to do. They may be able to send all these nasty packets to a system, but if you can make the system not be vulnerable to them, that's really important. Okay, yeah, so that's computer information in general. That you're sort of overlooking, IT hackers, networking people, qualified tech managers, chief security officers and chief technical officers, system administrators. Those are all under the umbrella of computer information. Okay. Any questions about computer information?
I have a couple questions I'll ask you after you're done.
Okay. All right, let's go into computer engineering. So computer engineering is a mix-mash of all of that, of the computer information, of electrical engineering, and of computer science. If you're a computer engineer, you have to have all of that background. So not only do you have to understand how to use all of this test equipment, and be able to understand, what the components are. But you have to also design how things are laid out. Does anyone know what this thing is in the top right? So this happens to be the processor architecture for a PlayStation 1, the first generation PlayStation. This is literally how the processor is laid out. And so a computer engineer would have to design this layout, and would then have to figure out, okay, I have this ALU, and this is doing addition, subtraction with the sign extension. It's doing the subtraction. So a bit's going to flip for the sign extension to specify a subtraction. It's doing multiplication, and there's no division. You're out of luck if you want to do division. And then you have to take this ALU, and then you have to say, okay, what component do I physically have to buy, and how do I physically connect it to all of these other stuff to make them do this behavior? So not only do you have to figure out, how are things connected in this sort of nice, pretty flowchart, but then having to figure out what component with what properties and what size and what pins is appropriate to put in that spot. So computer engineering is involving all of that. And so, yeah, you have to have this knowledge base of all of this, because now suddenly, if you're designing a processor for people to make games on or do anything with, you have to figure out, well, how are they going to program it? And you have to write firmware that allows them to be able to program this, to be able to make this, play video games. You look at this and you're just like, I see memory, I see things that do addition, subtraction, multiplication, and I see more memory. How do I take all of that and make something that renders graphics and makes pretty pictures and does all of that? So the computer engineer essentially has to write all of that code to take this bundle of components and gives them an interface that allows the developers to write something that does something useful. And so we typically call that firmware, something that sort of lives between the software that a computer scientist would write, and so it lives between that software, and it lives between and the hardware. So between the physical hardware and the software that the computer scientists develop, we call firmware. But really, it's just software, but it's at a much lower level. And it requires somebody like a computer engineer to actually understand what's going on. So even if you have a degree, a master's degree in computer science, you may not be able to even open up some basic firmware that was written for a fax machine and understand what's going on, because a lot of the code there has to do with directly interacting with the physical hardware that was selected by the engineer. So that's the three fields. We've got our computer science, computer information, and computer engineering. And it would be really helpful if all of these people talk to each other more. So wherever you go, try to diversify, try to talk to the different fields within whatever company you're in, so that you get an idea of where your piece of the puzzle fits in whatever problem that your company solves. That's really important. And that also helps add the feeling of value of what you're contributing. I know a lot of people, they feel really depressed when they don't understand how their code or how whatever they're doing for their work is beneficial to the company, because sometimes they're working on such a tiny piece of the puzzle that it doesn't really make sense. And so talking to other people and try to gain an appreciation with the various fields of people that you're working with, I think is really important. Okay, so I went to the cake store and they asked me what I wanted on the cake, and I said, oh, nothing. And then I came back to pick up the cake, and there's nothing on my cake. I was quite pissed off. And then the next time I'm like, okay, fine. I'm gonna actually have something. I have a picture. I want them put it on the cake. Ask me what I want on the cake. Hand them the flash drive, and there is my flash drive on the cake. not quite what I wanted, right? They literally interpreted what I was trying to communicate to them versus them trying to infer what I was trying to communicate to them. And really what I'm getting at is the word literally we misuse a lot. The word literally means that something is written exactly as it is meant to be interpreted. Something is either true or it is false. It is either 1 or it is 0. Computers are not good guessers. We have to tell them exactly what we expect from them, right? I have a household robot that wanders around the STEM center. It has some very clear instructions, ways that it can communicate with a human being. But imagine that you had a really, really bad day and you come home and you slough down on the couch and you're like, ugh, kill me, right? You don't want the computer or robot to interpret exactly what you just said, right? That there's a hidden meaning to indicate that you had a really bad day. And unless the computer or the robot has been programmed specifically for that case of when I hear somebody say kill me, they don't mean kill me, then suddenly it doesn't understand, if somebody's suicidal or if somebody had a bad day. It has no way of telling the difference between those. So computers are really not good guessers. And we have to keep that in mind when we're interacting with them, and that we have to, and we sort of, have to keep that in the back of our head when we're interacting with computers in general, is that right now, no matter how good they are, they can't really, they can't guess. They can make patterns, they can observe behavior and notice that they can associate given feedback. Like when you say kill me, you could keep giving it feedback saying, no, don't kill me. I mean that I have a bad day. Eventually you could have a machine learning algorithm that is able to adjust for that. But then when somebody actually is suicidal, it's going to have a much more difficult time separating the two. And so that's just something to be really, really mindful about. Okay, so I was being clever. Somebody asked me to make a gingerbread house, and I made them a gingerbread house. Went on. Okay. Okay. All right. So algorithms. An algorithm is a series of step-by-step procedures for performing calculations, processing data, or performing actions. I'm sure in your day-to-day life that you do something along of one of these. Right. You go from a sleeping state to waking up. You check your alarm clock. If it's too early, you go back to sleep. And you continue that cycle until finally you have to wake up and you stand up for your rights, right? Or that you have this flowchart for trying to figure out and debugging whether or not the lamp works. If it's plugged in, if it's not plugged in, you plug it in. If it's burnt out, you replace the bulb. If it still doesn't work after you've plugged it in and you've replaced the bulb, then buy yourself a new lamp. That you have these step-by-step instructions or processes of doing something. That's just an algorithm. That's stuff your brain's full of lots of vocabulary. That's my job here. So we see a prettier flow chart, right? So we've got our, there's thousands and thousands of different symbols, but I'm lazy. I'm just going to stick with these 4. So we've got our terminator, which is for starting and ending. We've got our process box, which is for doing stuff. We've got a decision diamond. Sometimes this is a triangle. This is for essentially branching off and taking different paths. And then we've got our input and output, or just I/O in general. So if we're consuming something or we're producing something, this is where we actually like ship it or whatnot. And then we connect all of these things with arrows. And so we have something like this, right? We have our terminator. We ask if we have homework. No, let's do some engineering stuff. And then we go back to asking if we have homework. Finally, if we have homework, then we go and can we procrastinate? Can we do it later? Then we screw around and we do engineering stuff, and then we continue the cycle. And then finally, if you can't do it later, you've done too much procrastinating, then you go do the homework. That's the process. And then the output, sorry about the screen. The output is you turn in the homework, and then you go back to asking if you have homework or not. And you notice that this is an endless cycle because there is no escape. There's always going to be homework. to do at some point. And so either if you don't have it at that moment, then you're going to screw around and do engineering stuff until you have homework. And so this is a chart that does not allow you to escape. Yeah, there you go. So there's a flowchart, and this is useful no matter what field you go into. I spend a lot of time doing box and arrow diagrams, flowcharts with computer science students, because it helps us break down and modularize the code and figure out, and it helps us visualize what's going on. And I think is really important, no matter if you're going into engineering and you're trying to communicate to another person what's going on, or how you're going to build something, that first this gets built and this is dependent on this, that you can illustrate that all with a flowchart. And back to the communication part, one of the companies that I worked for, I had an understanding of how things should be, like process-wise, of how we process authentication with smart cards, like those chip cards that we use for our credit cards nowadays. I was writing the procedures of how those transactions occur, and I was able to make a flowchart like 30 minutes. I made this very, very nice flowchart, and I was able to hand it to an engineer and say, here, build this device, code this device to work in this way. You plug in the card, you authenticate the card, you prompt for a PIN. They have, this is the cycle that they take, and that the developer then spent the next month building the hardware, so that it would support that. And then once they were done, they came back to me and said, okay, cool. We've now done with your flowchart. We now have a product that does what your flowchart says. And then I was able to take the same flowchart and the hardware, the physical device that they had built that was doing that, and I was able to hand that to an intern, just to a new quality assurance intern, and say, here, check this product against this flowchart and let me know if there's any issues. So I was able to pawn off several months of work by just making a simple flowchart that took me like 30 minutes to make. So flowcharts are a really nice way of being able to communicate and be able to delegate problems, as well as being able to break down a problem into these nice little chunks that's easier to understand. And so we can think of an algorithm just like a peanut butter and jelly sandwich. Probably should have started with that, but that you have, given a sequence of events that need to be done in the proper order, right? You can't eat the bread and then put the jelly on the bread, right? That doesn't make sense. So there's particular sequences of things that need to happen in a particular order in order to make sense. And there are some things that are not dependent on another. So for example, you could put the jelly on one piece of bread and the peanut butter on another piece of bread, but the order in which you do those isn't really dependent on each other. So there are certain actions that you can take alternate paths for, but in the end, that there's a sequential nature to it. So yeah, spread the jelly, slice of bread, peanut butter, stick them together, stuff it in your face. Pretty straightforward. And here's a Mindstorm robot that it happened to not know where the bread is, and it made a giant mess. That just happens. Okie dokie. All right, let's do some conditionals.
There's a pretty famous video of a dad messing with his kids trying to build a peanut butter and jelly sandwich, right? Or he has them write the instructions, but then he keeps messing it up.
Yeah. I had an instructor in junior high that we had an exercise where that's what she did, was like, hey, give me instructions one at a time. And so we're like, oh, you put the peanut butter on the bread, and she literally just picked up the jar of peanut butter and like slammed it on top of the loaf of bread still in its plastic. We're like, oh no, not that. Yeah, so that's always it's always fun.
Yeah, there you go.
Okay, let me do something one second. Okie dokie. All right, let's do some conditionals. So conditionals are statements that only run under certain conditions. This is a way that we're able to essentially change our behavior of our code based on input. And so I can't see any of you, but the idea being is that this would be a classroom exercise that I would be able to get everyone to either say hi or stand up. So if people were wearing black or white, that they would say hi and that everybody else would stand up. And so this would be a really easy way of being able to filter out the class of who's wearing black or white and who's not. And then out of paranoia, I would make sure that people would sit down. So I would say, if they like pizza, sit down. And there's always some smart ass that, that doesn't sit down. And so I always ask, if there's a whiteboard in the room, sit down. And so now I've guaranteed, that the room, the classroom at least, always has a whiteboard, because I also carry a whiteboard with me at all times. So there's always a whiteboard in the room. But this is a way of doing flow control, of being able to have people, interact, stand up, sit down, and whatnot. And so we see this when we go to like an ATM, when you hit one button versus the other, all that's happening in the background is these conditionals are happening. It says, if you press this button, then it's going to do this thing. And else, if you press some other button, it's going to do another check. Okay, so now we're able to combine those conditionals into these loop things. And so the loop is exactly what it sounds like. It's the action of doing something over and over again. So I'm sure that you have implemented this strategy with your parents or guardians at some point, where you were asking if you could have ice cream, right? You start off assuming the response is no. You ask them, can I have ice cream? If they say yes, then you're done. If they say no, you ask them, can I have ice cream? You are now trapped in this, they are now trapped in this infinite loop forever until finally they give up and yield you ice cream. Cool, cool. So yeah, can I have ice cream, can I have ice cream, can I have ice cream, until finally they say yes, and then you freedom. And so this is called a while loop. And then this one here, based on our age, is the number of times. So here's the input. This input is consumed once, whereas this input here was consumed every time you would ask, can I have ice cream? This input is consumed once. Based on our age, based on the age, is the number of times that we ask, are we there yet? The older we get, the more times we ask. We just get more clever at asking them. Like, have we arrived at our destination or whatnot? That the number of times the loop runs is the number of the input, and the input was the age in this case. And this is traditionally done with a for loop, but it doesn't necessarily have to be. Okay, so that's loops. Just so here is a loop that just runs indefinitely, assuming a response, versus this loop here runs based on a given number. Okay, so now let's fuse them. Let's mix those together. So we have this really nifty sandwich making robot here. The condition is, while I don't have 5 sandwiches, make a sandwich. So if it starts off with 0 sandwiches, how many sandwiches is it going to make?
It would start with 1, I guess, right?
Well, but look at the end, when it's done, when we finish this loop, how many sandwiches is it going to make if we start with 0?
Oh, you'll get 5.
Yeah, you'll get 5. And so then what happens if, while it's in the middle of making the second sandwich, I come by and I swoop and I eat the first sandwich? How many sandwiches is it going to make?
It'll keep making until you have 5.
Right. And so if I came by and I ate one of them when it was making the second one, how many sandwiches would it have? Would it have made?
Oh, I guess it'll make 6, you're saying, because you had to take one out,
Yeah.
but it'll keep going.
Right, exactly. And so, but what happens if it's finished making the fifth sandwich and I come by and I swoop and I eat the fifth sandwich?
Well, is it still checking, or did it say like now I'm done and then it stopped looping?
Right, so it's going to stop looping. So essentially, the moment this condition is true, it's done. So the moment it has 5 sandwiches, it's done, and then that code isn't running anymore. So it's going to only make the 5 sandwiches. So only if I eat the sandwiches while it's still making a sandwich, will it continue making more sandwiches. If I wanted it to run indefinitely, I could surround this with yet another loop that would run this all the time. That would be, maybe I change this to be an if. It would be like while true, and I would say just like, if I don't have 5 sandwiches, make a sandwich. Yeah, something like that. So yeah, a while loop is just going to run and it's going to be done the moment it's false. Okie dokie, artichoke. Yeah, so that's the fusion of our conditionals and our loops, is our ability to make sandwiches with the robots. Okay, so let's do a vocab check. What is a series of instructions on how to complete a task?
Algorithm.
Yes. And then what are statements that only run under certain circumstances?
Conditional.
Yes. And then what is the easy one? I should hear from everybody. What is the action of doing something over and over again?
Loop.
Loops. Yes, loops. All right. Oh, David, you have your hand up. Was there something?
I wanted you to, I guess, address the issue of infinite loops and how I guess that it's just a simple topic of I thought the robot example was going to that. What, maybe I missed it.
Well, so the ice cream example was an infinite loop where
yes, okay. Yeah.
where as long as the response is no, that it's an infinite loop.
Right.
Yeah. So for this here, we would surround this with a while true, something that just always evaluates to true, and then maybe inside of that loop we have a condition where we check, do we have 5 sandwiches? If we don't, then make a sandwich.
Right.
Okay. All right. Okay. Cool. All right. And then your brains are still malleable, so I'm going to pack in more information. So coding is just transforming actions into a symbolic language, or vice versa. So the idea being is that we have an action that we have in mind, like maybe we want to add 2 numbers to each other. That's the action. And the symbol that we use is that plus symbol to be able to indicate that. So yeah, all coding is us taking actions and then converting them into symbols that the computer or somebody else, even another human being, is considered coding. We see this in the medical world all the time, is that people have to, or even in the construction world, people memorize codes, right? There are these just numbers, and that they are associated with either actions or specifications for things, and that people are able to just talk about the number, the code number or ID, to each other, and that they understand each other. So that's called coding. Is just being able to take some kind of description or action and convert it into a symbol that other things understand, whether it's a human or a computer. Debugging is finding and fixing issues in the code. So it's a process, and that's pretty common. You've made a design of a bridge, and maybe it doesn't work exactly how you expected it to. The process of debugging would be to try to figure out what failed and why did it fail, and then going and fixing that. And then a function is a piece of code that can be called over and over again. So we're able to write code once, and we're able to essentially call it multiple times, and it does that thing multiple times. It would suck if every time we had to make a wheel, we had to start from scratch. So we're able to make generic code that's able to do that. And then on top of that, we're able to add parameters or arguments to that function. That's extra bits of information that allow us to customize it. It allows us to change the behavior of that function based on it. So imagine our microwave, Our microwave is in an infinite loop. We don't want our microwave to just stop working after a few times. So it's in an infinite loop, and it has a function that you type in, whatever numbers that you type in and hit start, the parameter is, or the arguments, or those numbers, how long you told it to cook is the parameters, and then the function itself is the cooking. And then maybe you have your temperature setting, you have your high, medium, and low. That's also a parameter that's get past the argument that will allow the microwave to change its behavior. Okie dokie. I do not have an Elmo with me. But yeah, let me just talk about this sort of in general. And so if we mix conditionals with real life, with like card games, right, we could do something like, if we drew a red card, we'd get +1. But with some knowledge of a deck of cards, what does this else cover?
It's about half the deck, right? So there's only black and white. I'm sorry, black and red.
Right, so what is that else covering?
All the black cards.
Yeah, exactly. And so one of the nifty things is we didn't have to explicitly write that, because we know that a deck of cards is strictly black and red. We can just say if it's red or else, and we know that that else is covering black cards. And so having some knowledge about the kind of data that we're working with can allow us to write things like this. What about this second one? What does this else cover?
Oh, I see. So it's just spades. You're saying like the last else doesn't really need a parameter.
Right, exactly. It doesn't need another one of these conditionals, because essentially imagine that this is a filtering mechanism, that if it gets caught up above, then we don't go down below. So if it's red, then +1 point. If it's clubs, minus 1 point. And what was this else? What was this 2 points? What did this cover?
It would be all the spades.
Yeah, exactly. So that would cover all the spades, and we don't have to specifically say that. But that with some knowledge of the kind of data of the cards, we're able to essentially make that assumption. Assuming we're not using like a French playing set of cards, that those barbarians have different colors and whatnot because they're French. Okay, so this is the activity that we would have done. So let's. I have a deck of cards. Let me just pull out some stuff out of it. Okay. All right. So I just pulled out a pile of random set of cards, and we're just going to do a few. Okay. So if I have, I guess I could do this. Let's see. Bink. All right. Okay. So, I should probably read the rules. And can all of you see my camera?
Yes.
Okay, cool. So all of you are on a team, and you're all against me. We're going to start at 10 points. So you're all at 10 points, and I'm all at 10 points. I'm going to use just some random cards that I just pull out of a deck. And then the team with the most points at the end wins. So where it says other team, that is me. And when it says your team, that's all of you together. So you're all responsible for keeping track of your score and my score. So I'm going to ask you frequently what my score is and what your score is. So is this lower than 9?
No, it's higher than 9. So it would go to Carter loses a point.
Okay, so what am I at now?
9.
Okay. All right, one more. Okay. What about this guy? What happens here? if I could backwards. What happens here? Is this lower than 9?
Yes, it's lower than 9. So we would go into the indented part of the if, and then it is black. So we get points equal. So we get 6. We get 6 points.
Yeah, exactly. So what are you at now?
So we are at 16.
Okay. What happens here?
Somebody else can do it. Come on.
Yeah. Come on, peeps. I've heard people talk. You have microphones. So is this lower than 9?
No.
Okay. So what happens?
Award other team 1 point. Wait,
Not
no,
quite.
sorry, we're not in that. Yeah. Else, other team loses 1 point.
Okay. So what am I at?
You're at. Well, I came in late. Somebody keep score in the chat.
So I lose a point. So what am I at?
Dave, can you help us out?
That was before your card there. So what just happened on yours?
So what just happened? Is it lower than 9?
No.
Okay. So what am I at now then?
He says you have 9 right now.
No, I was at 9. What am I at now?
8? You have 8?
Right, I have 8. Exactly.
Okay. I'm a little confused. Sorry, I came
Okay.
in a little late.
Right. Paige, you got it. Okay, what happens here? Is this lower than 9?
No.
Okay, and so what happens?
You
We
lose a
get
point.
the same number of points.
Not quite. Is
Oh.
it lower than 9?
Oh, if it is lower. No.
So what
Now
happens?
now you have 7.
I'm down to 7. I'm not doing so hot. Okay, what happens here?
It's lower
Is
than
this
than
lo-
9.
Yeah, okay, it's lower than 9. Is it black?
No.
Okay, so what happens?
Now
Award other
we
team
get a
1
point, so we get 17 now.
Reread that. Who's other team?
You.
Oh, other team is you. My bad.
Yeah. So
Now you get a point. So go back to 8. You get 8.
all right. I'm back at 8. Okay. Last card. What happens here?
It's lower than
Award
9.
other team 1. You get a point.
Okay. So what am I at?
9.
Okay. And so what are you at?
I think we had 16.
Yeah. So okay. So notice you guys won by a landslide. And was there any way with any configuration of a deck of cards that you could win, or that I could win?
Well, when were you getting points? Other was getting points on low reds. So if we had all low reds, you would win.
But what I'm saying is that a traditional deck of cards, if we went through this whole deck of cards with knowledge of how a deck of cards work, are you able to lose points ever?
No.
Right. And I am losing points at a much higher rate than I'm gaining points. And I can only gain and lose a point one at a time, versus you are gaining lots and lots of points.
Correct.
So who would always win given this configuration?
Our team.
Right, exactly, your team. And this is exactly what casinos do, right? They make up some kind of rules that look something like this. You may not see this, you may not see their conditionals, but this is what's happening in the background, and that they are able to adjust these, they're able to fine tune these to make them seem a little bit more fair. So maybe instead of 9, they turned it to a jack. and suddenly somebody went, oh yeah, that seems, that rule seems reasonable, and that they're willing to play it. When still the game is clearly designed around exploiting somebody who doesn't quite understand how the math works out. That in this case, the casino will always win if they were to flip this. So I rigged this so that you guys would always win. It would be very, very difficult for me just to pick out just a few random cards out of a deck and that somehow I would win. It is very, very unlikely. Yeah, so
craps is still fun. Come on.
Right, no, I love playing casino games. Luckily for me, at a very early age, I realized that I have terrible luck when money is involved, and I have decided to stay very, very far away from money involved casinos. But I happily will play poker and other games with people that are very much up to chance. But that it's really important to have some knowledge of how the deck is literally stacked against you. That maybe even the order in the deck that the deck is shuffled is rigged, but also that the rules of the game itself are in a way that makes it very, very difficult for you to win. Because the casino is a business. They got to make money. So just something to be mindful about.
It's probably wise.
Yeah. Okay. Let's see. All right. Let's talk about robots. Or I guess any questions about computer science before we move on? Everybody's all dandy, hunky-dory?
Everything's good.
All right. Let's talk about some robots. All right. Do any of you know who either of these are?
George Takei is not a robot.
Well, right. Okay, so we've identified one of the individuals in this picture.
Daft Punk, is that who that is?
Not quite. So this is R2. This is a robot that's up at the International Space Station. And we can see from the very sleek spot right here that hopefully that's not a human being that's super skinny. Okay. Yeah, so R2 is actually is a robot that's right now up at the International Space Station. They gave it some legs. But before I show you the legs, one of the biggest problems that astronauts had when they were working, when they were doing spacewalks up at the International Space Station, was that you pretty much spend your entire time holding onto the station with one hand and trying to do all of these operations like putting bolts in and screwing things down and whatnot with only one hand. So you're like trying to line up the bolt and then you're trying to like grab, have the screw gun and like put the screw gun on or put it on the bolt and then put the bolt where it needs to go. And so you see a lot of spacewalks where like they only undid a few bolts here and there and moved one thing to another thing, but that took hours because it was very, very difficult to do all of that stuff one-handed. And so originally when they built R2, they were thinking, oh, we'll just give R2 just a standard set of legs. And then once the torso part, the top part of R2 was up at the International Space Station and they were doing tests with it, they realized, wait a minute, the International Space Station is made with standardized railing inside and outside that could be used to grab onto the station. And so what they did instead was they built these legs that could fully articulate all around, and that the legs were specifically designed to be able to grab onto the railing of the space station. So now suddenly we have something that, the top half of the robot looks relatively humanish, but that this robot is actually able to perform much better in space because it's able to grab onto the station with its legs and is able to use its hands for what you should be using your hands for. And so I don't think R2's done any spacewalks yet, but R2's been up at the space station for a while. And the robot that I showed earlier, actually, I can just, So my camera would like to turn on. Camera. Yeah, the robot that I was showing earlier. I got Hopper here with me. Hopper actually runs the same operating system as R2 that's up at the International Space Station. Hopper here is running Robot Operating System, or ROS is what we call it. There we go. And link. There we go. Okay. And so actually also Curie that's wandering around in the STEM Center is also running Robot Operating System. That we have, this very cute looking household robot that's wandering around looking cute and making purring sounds when you pet it. And it's running the same exact base code as this very complicated robot that's essentially intended to replace humans in spacewalks. Because humans are precious things and can be damaged very easily. Resistor robot is a little bit more robust and can probably handle being hit by a meteor and survive, versus a human that's not quite the case. Right? I guess, is it an asteroid if it's still in space? Whatever. Okay. Micrometeor. Yeah. So the idea being is that this will hopefully eventually replace humans to be able to do very dangerous things. And that a human could also manually take over control and perform operations manually. Maybe they put on a set of gloves or something while they're inside the space station, or maybe they're down on Earth and they're physically able to manipulate the arms on the robot, but that the robot also is able to be fully autonomous. That if it was programmed to do an action, that it could then go and do that action automatically. Okie dokie. Yeah, so these are the two robots that I've been referring to a lot. This is Hopper. That's the one that's sitting right next to me. And so yeah, Hopper's job is to collect cubes, as I mentioned at the beginning. And then this is Curie. Curie is the cute little robot that's our current disease vector in the STEM Center. So I've stashed Curie away for the next 2 weeks. So hopefully she's not getting anybody sick. But yeah, she's just a little cute household robot that has a laser that uses for navigation. And she has a camera in her eyeballs to be able to determine whether or not people are looking at her or if they're smiling. And she also has code to detect if she's looking at a cat or a dog and things like that. Okay. So I sort of do a lot of generalization when I'm talking about robots. And so I like to break down robots into sort of two distinct categories. One category is remote control or tele robots. And this is where all of the decision making is human dependent. We also can consider the semi-autonomous, where maybe the human says, stay put. And maybe the robot is a quadcopter and it has to sort of float in the air, but it still has to do a ton of actions and do a ton of calculations to figure out how to stay put. So that's semi-autonomous. But that's still, I would consider remote control or tele-robot, because the decision-making is still very much on the human side. And so, like, for example, the bomb squad robot, that robot does not make anything up. It doesn't do any pre-programmed stuff. It only does exactly what the controller with a person behind the controls is doing, which is very, very important if you think about it. You don't want a robot just going into a dangerous situation like that and just randomly cutting wires, because that's what it's been programmed to do. Because then blame is really hard to assign. Versus bomb squad robot, which I'll show in a later slide. There's lots of people involved in it. There's not only the person behind the controller, but there's people typically standing behind the person who's behind the controller, giving them instructions, telling them what to open, what wire to cut, and things like that, where it's very much distributed. And then the other type of robot that we have are autonomous robots. And this is where all the decision making is based on the environment or other data input. So we see these Amazon fulfillment robots, that this robot, do I have yes, I do. Okay. Where this robot essentially is able to pull a database and say, okay, where does a shelf need to be? And then it puts itself into a queue, and then it goes and grabs that shelf and then goes and brings it over to a human picker. And the idea being is that there's no direct human interaction between the robot and the human. The closest thing to interaction is that the human presses a giant button that lets the system know, hey, I'm done picking out of the shelf. And that tells a robot, hey, if you're nearby, come and pick up the shelf and go put it back somewhere. So I have a video, and hopefully it doesn't look too terrible.
With that scale.
Just occurred to me that you are not going to be able to hear sound. Whatever, it doesn't matter. So yeah, you see these robots driving around these shelves, and essentially there's these giant screws that go up and down that pick up the shelf, and then they drive around, and they have these tags. Oh yeah, so we just saw a picker, whatever. Oh, we just saw a picker at the end. Come on, pause. It's not letting me. But essentially, what happens is it delivers these shelves to people, and then there's a little laser that then shines where in the shelf they need to grab it, and the human's role is literally just pull the thing out of the shelf and throw it in the box. And once they've done that, they hit a giant button that tells the robot that holds the box, hey, I'm done with that box. And it also tells the robot that's holding the shelf, hey, I'm done with that shelf. But then the robot may pick up that shelf and may go deliver that shelf to another picker, or might put it back into a spot in the warehouse like this. But the idea being is that you see hundreds and hundreds of these shelves, but there may only need to be a few robots to move all these shelving around. And it's nice because you suddenly don't have to have humans walking through all of this area. Not all of the Amazon spaces are like this. There are a lot of them that still require people to physically walk tens of miles every day to go pull stuff out of shelves, and then they have to carry that all back, and that's pretty tedious. So the idea being is that the human role is just pulling things out of a shelf and throwing it into a box. And eventually, and MIT is working on a gripper on a hand that should be able to do that action. But right now, sort of the most complicated process of this whole shipping procedure is literally just pulling something out of a shelf and putting it into a box. And so hopefully we'll have computers to be able to solve that problem, and the people that are working there can move to jobs that are less tedious on the body. Yeah, so there we go. We got manufacturing robots. Okay, another field of robotics that doesn't quite fit into those two categories is bionics. And bionics is essentially the method and systems that are found in nature, or are applying those biological methods and systems found in nature to the study and design of engineering systems and modern technology, and vice versa. So the idea being is that maybe we see things in nature and we use those ideas in engineering, but also maybe we have engineering ideas and we apply those to biological things. So, for example, I'm fairly certain that we have never seen in nature a pig with wheels. So we take this engineering concept and we apply it to a biological being, and it works out pretty well, actually. That would be bionics. Or maybe we see an insect and we choose to emulate that insect with electronics. Or we replace a limb with a bionic thing. I'm sure we're all familiar with exosuits. Maybe we've seen one of these things in one of those graphic novel things, or in those movie theater things. I believe we call this guy an Iron Man. And
yeah, that's him.
Yeah, that's him. That's him. Okay, just making sure. But we actually do have exosuits. There are some military exosuits that exist that I cannot show you pictures of. But then we have some consumer grade exosuits that allow people who would be otherwise wheelchair bound to actually be able to walk around. We also have right here, this is a cochlear implant. People who are born or maybe had meningitis at a young age, or maybe as an adult they lost their hearing. They're able to have a very intensive surgery where they're able to essentially have all of these electrodes glued to part of incisions that were made in the cochlear nerve that allows them to regain some sense of hearing. It's far from perfect. There are a lot of issues medically, but also culturally involved with the use of cochlear implants, but that they do serve a purpose. They do fulfill a role of giving people hearing again. But that suddenly now you have this interface to the brain where now maybe you could transmit other information. Many of these have Bluetooth connections or RF connections that allow them to be connected to things that are not, not connected to what our normal ears are connected to. And so right now they're still far from perfect, but the idea being is that, Neuralink, we see Elon Musk where we're able to have these implants that are able to solve things like seizures or other like Alzheimer's and things like that, that with implants that we could possibly mitigate, if not reverse, serious brain trauma and things like that. But also the idea being the Neuralink, eventually after they solve those problems, that they'll be able to move into maybe I'm able to access Wikipedia from just a thought. That would be pretty useful technology to have. So we see that this field of bionics definitely get a lot of attention, but then also a lot of people are fearful of such things. And just something to be really mindful. Some of this can be extremely dangerous, and some of this can be very beneficial for humans. And there are cultural impacts into both. Okay, so where do we see robots? We pretty much see robots everywhere. We see them in space. They beat us pretty much everywhere. Right? They're all over the place. And technically, like a satellite, a probe, it is technically a robot because it's able to move itself in an environment. Yeah, and it has sensors, so that pretty much makes it a robot. So yeah, we see it in space, we see it in manufacturing. The nice thing about robots is you don't have to pay them, and they don't really have to sleep. Out of a factory that's running, 24/7, the robots, essentially they power them down for like 4 hours every week, and that's just to reduce the electromagnetic fields that are developing in the factories. But otherwise, they're much more efficient than humans because they don't need sleep, you don't need to feed them, you don't need to pay them. They do require some maintenance, but that they don't get tired and they don't get bored of doing the same action over and over again. At least for now, we can appreciate that. But we also see cars. We see robotics popping up into cars. So this is a Google car, and there's the Tesla self-driving cars, and Ford has a license with the state of California to have a self-driving car, so that you don't even need to have a license. That you can just get into a car that has a license. The car itself has a driver's license. And personally, I'm a lot more willing to trust a car, self-driving car, than I am some teenager that has no experience driving on the road. Because imagine, the car gets into an accident because it made a mistake processing some information. Well, if the code is common across multiple cars, not only does the car have a lot more sensors than a human being does, but you're able to go and fix that mistake, and that mistake then applies to lots and lots of cars. So it improperly interprets where the line is of the road, and it runs one person off the road. Hopefully they're okay, but that that incident gets reported, and then they figure out, oh yeah, it improperly interpreted this, and then they write code and it solves that. They're now able to deploy that code to thousands and thousands of cars, and so all of those cars now have an improved performance. Versus a teenager doesn't see the edge of the road, drives off the road. If they survived, maybe they learned, and that one teenager is affected and learns and doesn't drive off the road right there. But all of the other teenagers who are coming in, or whoever's newly driving, they keep making the same mistake generation after generation. And so the self-driving cars, personally, I think that it's a pretty nifty idea, because it will allow us to very quickly and rapidly reduce the number of accidents that are occurring, and make people much safer. but I do definitely understand the negative ramifications of that. That somebody could be malicious and tell a car to go slower or cause it to drive to drive into a ditch or whatever. But even modern cars with the little where the wheel shakes a little bit when you are in the wrong lane or whatever, that those cars can already be hacked. So it doesn't even have to have a self-driving element in order for somebody to hack into the car and to drive it into a ditch. There's a great article in the Wired magazine where the reporter essentially told some guys who work for Twitter, "Hey, go for it, hack my car." And they were in another state. They hacked into his Jeep. They changed the picture on the stereo to their face. They engaged the cruise control and locked him out of the speed control of his car, and they drove him into a ditch. He was okay. He was very frightened about the thing. He had given them permission to hack into his car, but he didn't think that they could actually really do it. And car manufacturers have been notified that pretty much all modern cars have these vulnerabilities. But the car manufacturers, they've already bought all the computers and all of the software that they're going to use for the next 10 years of computers. So they're not going to fix those issues for another 10 years. So just be mindful when you're buying new cars. Not to make anyone really afraid, but that's just the world we live in, where things were built improperly without the intent, without the thought that somebody could be malicious when communicating with a car. And so the same thing is that a modern car made in the last 20 years, you could pop out the tail light, plug in a computer into it, and tell the car to unlock itself and then to start up the engine. That's a pretty straightforward task for a modern car. So people who have, and that's only about $100 worth of equipment to do that. I'm not suggesting anyone do that. I just want you guys to be mindful of how easy it is, and to hopefully don't be too paranoid, but just be mindful that things are easy to break into. Okay, and then we also see robots in the medical world and in agriculture. So we already did flowcharts. We're not doing my robotic friends. So robots can be used for funsies, right? For solving for Rubik's cubes in record times, right?
Oh yeah, they can do it in like 2 seconds or something,
0.8
right?
seconds.
Yeah, wow.
But also the robot can be really good at playing really bad soccer. Right. Hopefully the goalie is just really garbage. That helps a lot. But one of the most more impressive things about this robot is its ability to open a container. That's very, very easy task for us humans, but it's a very, very difficult task for robots. Okay, I only got a few minutes left, so let me sort of blast through this. So human-robot interfaces. So we see lots of ways that we can interact with robots. We've got our Xbox controllers. Actually, this robot next to me, when I'm testing it in a semi-autonomous mode, I can plug in an Xbox 360 controller into it to test the engine, to test the motors, and to test the grabber. But here's a bomb squad robot controller for a robot, where we've got the radio and we've got the controllers and the headpiece. And this involves a team, right? There's one person at the controls, but then there's people behind them that are doing stuff. Then in RC, you've got a little remote control car. Right, you would be controlling with this guy, so that would just be one person. But then maybe if you're controlling a rover on some planet or something like that, you need a team. That maybe an entire row of these people, their entire job is just moving one of the arms, and another team, another group of another entire row is people of just scientists saying, "Hey, it'd be really nifty if we could go look at that rock." And then maybe there's this team here that their whole job is to just move the gripper to grab the rock. And then there's this team all the way over here that has some kind of laser that vaporizes the rock and then uses the sensors to report the color of the vaporization and then reports that back to that science team. So it took all of these people here just to go grab a rock extend the arm, pick up a rock, vaporize it, and look at the science. It took all of these people to do that. And it's really important to be able to work as a team because people are able to check each other. If somebody made a mistake, with a robot out there, if the arm collides with itself, if the arm collides with itself, you could do permanent damage, and that would then cause the robot to not work anymore. Maybe you damage one of the wheels, now the robot is stuck there. Or you damage the arm, now it can no longer interpret that kind of sensor data. So being part of a team is really important for helping distribute the load of who's doing what, but also for checking for errors. Robots have lots of different kinds of sensors. They have particle detectors like Geiger counters and smoke detectors. They can detect weather, like pressure, heat, water, solar radiation, things like that. One of the nifty things is that their cameras can see far more than what we can see. So for example, if your TV remote is not working and you're trying to figure it out, you could turn on the camera on your phone, and you can point the remote at your phone and press a button on the remote, and you should, on the screen of your phone, see the ultraviolet light. Because what happens is that the screen on the phone only displays frequencies that our human eyeballs can see, but the camera on the phone, it has a much wider frequency range. You can see infrared and ultraviolet. And so it essentially is forced to interpret what it sees with the camera to something that our eyeballs can see. And so that means that these robots are able to make much better decisions than we can because they can see more than we can. Like if you've ever seen like a video of what a bee sees or what a bird sees, like the colors are much more vibrant, and some of them, some flowers have like landing strips on them. When we look at them, they just look like dull flowers. So being able to see more means that we have more information to be able to make better decisions with. Also, that means that maybe you could mark the roads with like a center line for the road with something that is not visible to humans, but would be visible to a robot to be able to make it behave better. So things like that. And then we've got like pressure sensors, like bumper switches, and then feedback. Feedback could be that the robot performed an action, like it turned its wheel, and that it needs to know how much did it actually turn its wheel by. There's things called light encoders that essentially send pulses of how much did I see the wheel turn by, and then it's able to then change its behavior based on that. But feedback could also be provided from a human, saying, good robot or bad robot or whatever. And then we've got sonar, radar, and lasers. And that's what this dome is on top of this Google car, is that this is sending out a ton of lasers all over the place, and it's seeing where they bounce, and then that helps it decide what it's looking at. And there's tons of other kinds of data. Movement, there's lots of different ways that robots are able to move. We've got our servos up here. We've got our DC motor. We've got hydraulics like tractors. We've got our plasma propulsion that we see on satellites. We've got our electromagnetism for being able to move things or move themselves. Robots don't necessarily have to be able to move themselves. Maybe they just have to move their environment around them. So that's one of the things about a robot, is that a robot has to have sensors and it has to have some form of movement. Either it's moving itself in its environment or it's moving things in its environment. And that's what it makes it a robot. Just a quick engineering thing. Gears are really cool things. They allow us to change the direction. So here, if this was running properly, one gear would spin the other way, and then one way, and then the other gear would spin the other way. But also, if we change the size of them, they allow us to change the speed. Oh, and this symbol here is delta, which just means change. If we change the size, we're able to change the speed and the torque. And so if you ever used like a bicycle that's a cruiser, going uphill is really, really hard with a cruiser bike. But if you have a ton of gears, you can change the ratio, the sizing of these gears, and that can make your life much easier. Pulleys are really useful. They allow us to change the direction of force. So essentially, I'm able to pull down, and that picks this thing up. But one of the nifty things about pulleys is that as we add them, it essentially reduces the amount of force that we have to apply, but increases the distance. So if we add 2 pulleys, say this is a 100-pound weight, I only have to pull down with 50 pounds, but I travel twice as much. And then if I add 4 things, then I essentially pull with 25 pounds, and I go 4 times the distance. So pulleys are really useful things, sort of out of the scope of this, but that's it. And this is another one of the activities that we would have done, but that's, we're not physically there. Okay, so that's pretty much all I got for, we're not going to do Arduinos because we're out of time. But any questions about anything?
Did you say the Robotics Club was already disbanded, or what was that? What was your conclusion on that?
Oh, so the Robotics Club is still meeting, but right now, sort of nothing's happening because of the plague. But the competition that was happening, the Swarmathon, I was dealing with the robot that I'm sitting next to. That competition is over, but the Robotics Club is still very much active. They're working. They're doing an Amazon competition, teaching a race car how to drive around a racetrack, and they were looking at starting a MATE team, but MATE was canceled this year due to that's a ROV underwater robotics competition that was canceled due to the plague. And yeah, so the Robotics Club is very much active and is very much interested in new members and new things to do.
That's cool. Thank you.
And so there's a Facebook, and then there's an email. If you blast an email to that saying, "Hey, sign me up," then Maureen will set you up.
All right.
Thank you.
Yeah.
Yeah, that was very cool, Carter. Thanks a lot.
Yeah, thank you.
You're welcome.
I will email you if I have further questions. I just had I guess a couple thoughts about I guess information systems in general. I just wanted to get more into the field. I've considered taking like IT accreditation courses, like the A+, like the TIA thing. What do you have to say about that?
Yeah, so that's a CIS 170, or 171, I think. We just merged those. And that's taught by Marcelo. Marcelo is a fantastic instructor. He's great. He's a lot of fun. And that's going to give you a lot of hands-on experience with physically building computers and debugging and figuring out how to fix them and whatnot. So so that's a great class. And that fairly well prepares you for the A+ certification. And if you talk to Marcelo about it, he has practice exams, and we also have a discount through the CIS department for that test. So if you do want to go through and jump through that test, we do have a discount. We do have practice tests, and we have material to help you out with that.
I see. Thank you.
Are you teaching all day, or you have other classes today?
So I had I was teaching this morning Java, and then I'm doing so I have to do a bit of cleanup for the Java class this afternoon, and then tonight I have the night class for Engineering 5 that I'm doing.
Right on. Well, cool, man. It was nice seeing what you're doing. This looks really neat.
Thanks. Yeah, good luck with engineering.
Yeah, thanks. It's it's a lesson for you. It's never too late to go back to school.
Yep.
Right on. Have a good one.
Yep. See you around.